What invisible force guides the universe's endless dance? How do cosmic collisions create and destroy in the same breath? What stories did the first galaxies write when they merged in the universe's youth? In the grand cosmic arena, nothing is truly still. What seems like a silent, motionless sky is in fact alive with movement on a scale that's hard to fathom. The universe is a continuous ballet of drifting galaxies and whirling stars, a symphony of perpetual motion where every cosmic object plays its part. When we gaze up at night, the stars appear fixed in place, twinkling quietly as if pinned on a black canvas. But this stillness is an illusion of our short lives and limited perspective. In reality, even the fixed stars are racing through space, each following its own path. Here on Earth we barely notice, but our planet is spinning on its axis and hurtling around the sun. With every passing second, we're carried thousands of kilometers through space on Earth's yearly orbit. Yet that's only the beginning of our journey. The sun itself is not static. It leads our entire solar system in a great orbit around the center of the Milky Way galaxy. This galactic voyage is almost unimaginable in scale. A single circuit takes about 225 million years. In other words, the last time our sun was at this point in its galactic path, dinosaurs roamed an Earth that looked very different. We are passengers on this slow, colossal ride, moving through different regions of the galaxy and rarely even aware of it. And the motion doesn't stop there. Every star you see, every distant cloud of gas, and every galaxy beyond our own is also in motion. Our Milky Way galaxy rotates majestically, its spiral arms sweeping through space. At the same time, the Milky Way is being gently pulled and tugged by the gravity of its neighbours. Our galaxy and the Andromeda galaxy next door are actually on a slow-motion collision course, a galactic tango unfolding over billions of years. In roughly 4 billion years, these two giant star cities will meet and merge, reshaping both into a single, larger galaxy. It's a dramatic destiny. Yet it is happening so gradually that from our vantage point, night after night, Andromeda only appears as a faint smudge in the sky, inching ever so subtly closer. On even larger scales, the entire universe itself is expanding. Distant galaxies are spreading apart from each other as space stretches between them. This expansion is often compared to a dance as well, not a frenetic dance, but a slow waltz driven by a mysterious force pushing the cosmos outward. Galaxies follow paths determined by gravity and the echoes of the Big Bang, some congregating clusters bound together, while others drift into the vast darkness. Every galaxy carries on its journey, swayed by the gravitational influence of its neighbours and the overall expansion of space. All of this motion, the spinning of planets, the orbiting of stars, the merging of galaxies, the expansion of space, is the backdrop to everything. Change and movement are the universe's most enduring features. In this endless cosmic dance, worlds are brought together and torn apart. How do all these disparate movements harmonize? What invisible hand guides the planets in their orbits and draws galaxies into collisions over eons? To understand the choreography of this cosmic ballet, we must look to the subtle yet all-powerful force that underlies it all. We turn now to gravity, the great weaver of the cosmos, whose gentle pull directs the movements of planets, stars, and galaxies alike, the unseen conductor guiding the dance of the universe. Gravity is the master choreographer of this cosmic dance. It is an invisible bond, a gentle yet inexorable tug that every piece of matter exerts on every other. This force is subtle. We don't notice the pull between our own bodies and a distant star, for instance. But across vast scales, gravity is the architect of structure and motion. Without it, everything would drift aimlessly in straight lines. With gravity, paths curve and dancers in the cosmos embrace. Planets are held in orbit around stars by this balance of forces, the inward pull of gravity and the outward push of their motion. This delicate equilibrium keeps Earth bound to the Sun and the Moon bound to Earth, all whirling in a silent rhythm. When that balance is disturbed, gravity shows its more dramatic side. If a planet or a star strays too close to another massive object, the steady orbit can tighten or unravel. A passing star might send a comet flying into the inner solar system, or a massive world like Jupiter might fling smaller bodies out into interstellar space. In the cosmic ballet, gravity can be both nurturing and disruptive, ensuring some bodies move in orderly loops, while others are nudged onto new trajectories. Many galaxies, for example, are locked in gravitational dances with their neighbours, destined to meet and merge because they cannot escape each other's pull. Over time, their orbits shrink and their fates intertwine, drawn together by an attraction that only grows stronger as they come closer. When two massive objects meet under gravity's guidance, the encounter can be gentle or catastrophic, but it is always transformative. Sometimes two passing stars might merely bend each other's paths, slingshotting away to continue on alone. Other times, they may become bound in a tight orbit, twirling around a common center as a new binary star pair. And occasionally, especially in dense regions of space, two stars may fall directly toward one another and collide, merging into a single, brighter star. Imagine such a meeting. Two suns converging after eons of separate journeys, touching off a burst of light as they unite. These events are rare in our current universe, but in clusters crowded with stars, they do occur, further proving gravity's power to connect and reshape cosmic entities. On a grander scale, gravity orchestrates the encounters of galaxies. When one galaxy drifts near another, their mutual gravity reaches across the void. Even before any direct collision, the force begins to tug on stars and clouds of gas, slowing the galaxy's motion like a cosmic brake. If they draw close enough, they might enter a slow spiral around each other, like partners preparing for a dance. Over millions of years, that spiral tightens. The galaxies swing past one another, their shapes distorted by tidal forces, and eventually they coalesce. In that prolonged encounter, gravity can wreak havoc, but also spark creation. As two galaxies entwine, their gas clouds slam together and compress, igniting furious episodes of star birth amid the chaos. One galaxy's gravity might even trigger a burst of new stars in its partner, as happened when a massive spiral galaxy warped a smaller companion and set it ablaze with star formation. Under gravity's influence, serene cosmic structures can suddenly light up with the fires of millions of newborn suns. Gravity's influence in these encounters isn't limited to creating new stars. It can also tear things apart. A vast galaxy pulling on a tiny dwarf galaxy might slowly shred the smaller one, pulling streams of its stars loose and scattering them into space. Stellar systems can be ripped from their homes and sent wandering. Yet even in destruction, gravity weaves new patterns. The stars stripped from a disrupted galaxy may wrap around the larger galaxy in ghostly tidal streams, or they may regroup to form new clusters, finding a new place in the cosmic tapestry. In this way, gravity acts like both an artist and a storyteller. It breaks the old forms and sculpts new ones from the debris, ensuring the drama of creation continues. Through all of these gravitational encounters, one theme emerges. The universe is bound together by an ever-present attraction. It pulls together drifting matter to form structure, and it pulls together structures to form even larger ones. Without gravity's guiding hand, the cosmos would lack the grand collisions and mergers that shape galaxies and trigger new stars. It is gravity that set the stage for the very first collisions in the young universe's crowded beginnings. In that early epoch, matter was closer together, and gravity's work was on full display. Countless nascent galaxies drawn together, merging and assembling the first large structures. Now, having explored gravity's role as the cosmic matchmaker, we travel back to those tumultuous early times to witness the first great collisions that sculpted the universe shortly after the dawn of time. Not long after the universe was born, the stage was set for the first great cosmic collisions. In that epoch, everything was closer together. The cosmos was smaller, denser, and brimming with newborn stars. Around 200 million years after the Big Bang, the very first stars ignited out of primordial clouds of hydrogen and helium. These pioneer stars gathered into tiny protogalaxies, galactic infants glimmering in the darkness. Space between galaxies was much tighter then than it is now, so these young galaxies didn't stay isolated for long. Drawn by gravity, they began to converge and clump, merging with their neighbours. The structure of the universe was built this way. Small, baby galaxies steadily colliding and combining to form larger and larger galaxies. It was a time of rapid growth, a cosmic adolescence full of fireworks. One can imagine the scene billions of years ago. Countless miniature galaxies drifting through space, each teeming with hot blue stars, slowly being pulled toward one another. When two of these proto-galaxies met, it was not a gentle affair. They crashed together in slow motion, stars and gas clouds intermingling and jolting under gravitational forces. Unlike later cosmic collisions that might involve well-structured spirals, these early smash-ups often involved irregular, amorphous collections of stars. As they merged, chaos gave birth to brilliance. Gas clouds within the colliding galaxies were violently compressed, triggering gravitational shockwaves that rolled through the galaxy's cores. In their wake, these shockwaves left whole clusters of newborn stars. Each collision was like a cosmic forge, creating new stars by the tens of thousands in a sudden burst. The night sky of that era must have been ablaze with star formation wherever galaxies collided. These early mergers built up galaxies in a hurry. Over relatively short spans, on the order of a few 100 million years, small galaxies would coalesce into much larger ones. By the time the universe was only about 3 billion years old, astronomers find galaxies that are already enormous, rivaling the size of today's giant galaxies. It was a great cosmic surprise. Some of these early massive galaxies were packed so densely with stars that they were 3 times smaller in size than similar mass galaxies today, yet contained just as many stars. Imagine a galaxy with the mass of the Milky Way, but crammed into a volume only a fraction of the Milky Way's, its stars pressed together like a bustling crowd. These galaxies weren't forming new stars anymore. They had burned through their fuel. In the young universe, they were already dead galaxies, filled with old stars. How could such giants form so quickly and use up their gas so fast? The answer seems to lie in extreme collisions and frenzied star formation. When astronomers study these ancient heavyweights, they see signs of violent origins. One scenario becomes clear. If 2 or more gas-rich galaxies crashed into one another early on, The combined torrent of gas could have funneled into the center of the merger, triggering a stupendous burst of star formation. For a brief time, perhaps only tens of millions of years, stars would be forming at a furious rate in the heart of the new galaxy. So intense was this starburst that it rapidly consumed the available gas. The merger might also have blown out some gas in gigantic stellar winds or supernova explosions. In the end, the merged galaxy was left virtually gas-empty, a colossal assemblage of stars with no raw material to make more. It became a cosmic metropolis that had effectively burnt itself out in childhood. Such galaxies, resembling elliptical galaxies rather than spirals, were no longer birthing stars, even though the universe was still young. They stand as fossil evidence of how dramatic and efficient those early collisions were at building up cosmic structure. While two galaxy mergers were common, sometimes even grander collisions took place. Recent observations have uncovered extraordinary pile-ups of galaxies in the ancient universe. For instance, the James Webb Space Telescope recently spotted a rare crash involving not just 2 or 3, but 5 galaxies all merging together, only about 800 million years after the Big Bang. Finding such a 5-galaxy pile-up so early in time highlights just how crucial mergers were in shaping the first generation of large galaxies. In that single event, multiple galactic fragments likely coalesced into one, stirring up an enormous halo of stars and gas. It's a scene of almost unimaginable grandeur. 5 infant galaxies caught in each other's embrace, spinning together inside a common cloud of gas and emerging as one brighter, more massive galaxy. Though such complex collisions are thought to be rare, they underscore the chaotic environment of the early cosmos. By merging and assembling, these formative collisions wrote the opening chapters of galactic history. Every large galaxy today, spiral or elliptical, likely has an ancestry that traces back to those initial mergers. The Milky Way, for instance, is built from the remnants of many smaller galaxies that merged over billions of years. But it was in the universe's first couple of billion years that this process was most rapid and prolific. Countless smaller units came together, giving rise to bigger structures at an astonishing pace. The debris and energy from those collisions enriched the surrounding space with heavier elements forged in the flurry of new stars. In that sense, those first collisions didn't just shape the outline of galaxies. They seeded future possibilities. They filled galaxies with stars and starlight, and sprinkled the ingredients that would one day form planets, and perhaps life. The universe's youthful chaos eventually began to settle. As the cosmos expanded further, collisions became less frequent. Galaxies grew larger and more isolated in the vastness of space. But the legacy of those early smash-ups endures in the galaxies around us. The next time we look up at a galaxy through a telescope, we might remember that its smooth glow could be the aftermath of ancient collisions long past. And as we move forward in cosmic time, collisions still continue, but at a gentler pace compared to that wild younger epoch. Even so, in star clusters and busy galactic hubs, encounters never stopped entirely. We now turn to those dense swarms of stars, clusters where the chaos of close encounters persists, to see what happens when hundreds of thousands of stars crowd into a small cosmic space. In contrast to the vast emptiness between galaxies, star clusters are like crowded cities of stars, where chaos reigns on smaller scales. A star cluster, especially the young and massive kind, can pack hundreds of thousands of stars into a space that would be considered a mere dot by galactic standards. Imagine a swarm of suns so close together that the distance between neighboring stars might be only a few trillion kilometers. By astronomical reckoning, that's incredibly near. In fact, a region of space where stars are only a few times the Earth-Pluto distance apart is considered outrageously crowded by astronomers. In such dense clusters, stars are separated by barely a whisper of space. From within one, the sky would be filled with brilliant stellar lights in every direction, far more intense than any night sky seen from Earth. In these crowded stellar cities, gravity plays a frenetic game. Each star moves in the cluster's gravitational field, which is the collective pull of all the others. Paths are far from orderly. A star speeding along on one trajectory may feel the tug of several neighbours, causing it to veer onto a new course. Encounters are frequent. One star might swing past another, and though they're unlikely to collide outright most of the time, their mutual gravity can slingshot them onto completely different orbits. In some cases, a close three-star encounter can send one star rocketing out of the cluster entirely, exiled to drift in the galactic field alone. The remaining stars from such an encounter might settle into a tight, binary orbit, now bound as partners. Over millions of years, this gravitational dance slowly alters the cluster's makeup. Stars exchange energy like dancers swapping partners. Some migrate toward the cluster center, while others gain speed and escape the cluster's hold. Bit by bit, the cluster can shed stars, thinning out as its most adventurous members are flung away. Once in a rare while, though, two stars in a cluster do meet face to face. With so many stars in close quarters, given enough time, an actual collision becomes almost inevitable. In the cores of globular clusters, those ancient, tightly packed spheres of stars, astronomers estimate that stellar collisions happen roughly once every 10,000 years on average. It's an infrequent event on human timescales, but in the life of a cluster, which can be billions of years old, such collisions add up. When two stars collide, the event is extraordinary. Typically, the two stars will merge together, forming a single, more massive star. The violence of their union can produce a sudden flare of light. The new star may burn hotter and bluer, appearing unusually youthful compared to its brethren. Indeed, astronomers observing old clusters often find mysterious blue stars among an otherwise aged stellar population. These blue stragglers are thought to be the products of stellar mergers, old stars reborn with fresh energy, standing out as renegades that seem younger than they should. In a sense, the cluster's chaotic gravity can rejuvenate some stars by smashing them together. Modern simulations of star cluster evolution show just how intense these environments can be. In one simulation of a young massive cluster forming during a galaxy collision, researchers tracked dozens of stellar collisions over just a few million years. Among them, they noted collisions involving stars dozens of times heavier than our Sun. Imagine two massive suns spiraling into each other. As they merge, they could form an even mightier star, or perhaps collapse into a black hole, or trigger a stupendous explosion. Such events would be fireworks on a scale beyond imagination, momentarily outshining entire star clusters. Though these dramatic collisions are not everyday occurrences, the fact that they happen at all reminds us how energetic the cluster environment is. Meanwhile, countless near misses and close passes are happening all the time. Each close encounter redistributes momentum between stars, a gradual churning that keeps the cluster dynamically alive. For any planets that might be orbiting stars in these clusters, the chaos can be disastrous. A star wandering too close could yank planets from their orbits or perturb them into unstable paths. The concept of a peaceful, long-lived solar system like ours is almost unthinkable in the hubbub of a rich cluster. The gravitational influence of so many nearby suns would wreak havoc on planetary orbits. Yet amid the disorder, the cluster as a whole remains bound together, a gravitational family. Over time, it may expand and relax as interactions spread out the stars. Some clusters will eventually dissolve completely, their members drifting away to join the general stellar population of the galaxy. Others, especially massive ones, can survive for billions of years, gradually burning off energy through interactions, but still remaining recognizable swarms of stars orbiting their galactic center. From afar, a dense star cluster looks tranquil, a glittering ball of light. But as we've seen, up close, it is anything but tranquil. It is a constantly shifting arena of gravity where stars can be deflected, exiled, or even fused together. This microcosm of cosmic interactions teaches us that not all collisions are between galaxies or giant entities. Sometimes, gravity's havoc is playing out on a much more human scale, astronomically speaking. And even beyond the clusters, there are subtle, almost invisible gravitational dances happening in more diffuse settings. Many cosmic orbits that appear stable and calm are in fact slowly evolving, inching objects toward future encounters. The next chapter in our journey takes us into this realm of deceptively gentle motions, the slow ballet of orbits that, over eons, can ultimately lead to spectacular conclusions. Orbits are nature's compromise, the balance between moving forward and falling inward. A planet circling a star, or a moon circling a planet, may seem to trace the same path endlessly, year after year. This slow cosmic waltz can persist for millions or billions of years, with very little change. From our perspective, an orbit appears almost eternal. Earth has looped around the Sun about 4.5 billion times after all. But look closer, and even these graceful motions are not absolutely permanent. Subtle forces are at work, gently tugging at the dance, altering it on near imperceptible timescales. Every orbit is a little tug-of-war between gravity and inertia, and sometimes one side eventually gains the upper hand. Consider a humble moon like Phobos, the tiny inner moon of Mars. Phobos races around Mars faster than Mars rotates, creating a gravitational tide that saps orbital energy. With each passing century, Phobos spirals a few meters closer to Mars. It's a minuscule creep inward, but inexorable. Given enough time, the moon's fate is sealed. In roughly 30 to 50 million years, Phobos will be torn apart by Mars's gravity, possibly forming a ring, or else crash piece by piece into the Martian surface. What seems today like a stable, quiet orbit is actually a slow-motion fall. Tidal forces, the same kind that make ocean tides on Earth, are robbing Phobos of its stability. The moon's very structure is already showing signs of this strain, with long grooves on its surface likely serving as stretch marks, foreshadowing its eventual breakup. Even in systems where no tides or friction are apparent, orbits can decay through more subtle means. Two stars orbiting each other in the void of space might seem destined to circle forever. Yet if those stars are very close or very massive, they emit gravitational waves, ripples in spacetime that carry energy away from the orbit. This loss of energy translates into a gradual tightening of the orbit. A famous example is the Hulse-Taylor binary pulsar, a pair of dense neutron stars whirling around each other. Astronomers have observed its orbital period shrinking ever so slightly, exactly as Einstein's theory of gravity predicts, due to gravitational wave emission. The change is on the order of seconds over many years. Barely noticeable, yet undeniably real. In about 300 million years, if nothing else intervenes, those two stars will spiral into each other. In 2017, scientists detected gravitational waves from just such an event. Two neutron stars that had been doing their orbital dance for eons finally collided, unleashing a flood of energy and forging heavy elements in the process. On an even grander scale, galaxies themselves experience a slow dance that ends in union. Our Milky Way and the Andromeda Galaxy, as we've noted, are approaching each other on an orbital path that will close over the next few billion years. At first, they will likely sweep around one another, perhaps even completing a loop like partners in a cosmic ballroom. But gravitational forces will inexorably draw them together until the two merge into one. In the meantime, each pass strips a bit of momentum from their orbit. Even without an outside influence, their mutual gravity ensures that what starts as a leisurely orbit ends in a merger. The same principle is observed in smaller systems. For instance, many stars have been found in elongated orbits around the massive black hole at our galaxy's center. Over time, interactions and gravitational radiation can nudge those orbits, and occasionally a star plunges inward, perhaps to be swallowed by the black hole or flung out of the galactic core at tremendous speed. No orbit is perfectly fixed. Given enough time, gravitational choreography can change the steps. The slow ballet of orbits is deceptive. For countless cycles, nothing dramatic seems to happen. A moon rises and sets, a binary star eclipses like clockwork, a galaxy drifts around its neighbor, and the stability can lull us into thinking it will continue forever. But the universe rewards long patience. Tiny perturbations accumulate. A distant encounter, a faint drag, a minuscule gravitational ripple. They can all add up over millennia and millions of millennia. Then one day, the graceful dance becomes a dramatic finale, a collision, a merger, an infalling crash. When that moment comes, the orbit that once embodied harmony turns into an agent of profound change. Two bodies that spent ages circling each other finally meet, and both are forever transformed. In this way, even the calmest orbital dance hides an ending. It might be an explosive one, two stars merging in a blinding flash, or a planet spiraling into its star, or a quiet subsumption, like a moon slowly disintegrating into a planetary ring. Every orbit carries the seeds of a future collision or dispersal, given enough time and the right conditions. And when those encounters occur, they often leave their mark on the cosmos. We now venture into examining those marks, the structures and shapes that cosmic collisions create. In the next part, we'll see how galaxies colliding can be like sculptors' hands, molding matter into tails, rings, and bridges of starlight, and how each encounter imprints a story onto the galaxies involved. When galaxies collide, or even just brush past one another, they often leave behind spectacular evidence of their encounter. Gravity doesn't just pull galaxies together, it stretches and warps them, molding their shapes like cosmic taffy. In a close galactic flyby, for instance, the two participants rarely hit head-on. Instead, they swing around each other, and during this brief orbital pirouette, each galaxy's gravity draws out the other's stars and gas into elongated streams. These are the famous tidal tails, long, often curved ribbons of starlight flung into intergalactic space. Picture a spiral galaxy having its arms yanked outward. As its partner galaxy pulls on it, one side of the spiral is drawn toward the intruder, and the opposite side is flung outward, creating a tail. At the same time, material can be pulled between the galaxies, forming a connecting bridge. Just as the moon raises two tidal bulges on Earth's oceans, a galactic encounter raises two stellar tides on each galaxy, one trailing behind as a tail, and one bridging toward the other galaxy. These tidal tails and bridges are like signatures of the encounter, sweeping out tens or even hundreds of thousands of light years. Some of the most arresting images in astronomy are of these tidal structures. The antennae galaxies, for example, are two merging galaxies whose encounter has flung out dual tails that resemble insect antennae arcing into space. Those tails are studded with bluish patches, clusters of young stars that burst into being amid the collision's debris. It's common for tidal tails to glow with such new star formation. When gas is ripped out of galaxies, it can clump and collapse into stars in the tail's wake. Another striking case is the mice galaxies, a pair of spirals caught in a gravitational embrace, each sporting a long, thin tail of stars drawn out by the other's pull. These tails curve gracefully, testifying to the past orbits the galaxies took around one another. They are snapshots of galaxies in mid-collision, with matter literally being sculpted into extrusions. Not every galactic encounter produces photogenic tails. The outcome depends on angles, speeds, and the types of galaxies involved. But distortions of some kind are almost always present. If one galaxy is much more massive than its companion, the smaller galaxy might be shredded completely. In such cases, instead of two prominent tidal tails, the larger galaxy may end up with only a faint stellar stream as the remains of its victim. A bridge of stars might briefly link them before merging into the bigger system. Often, the larger galaxy will continue on, relatively intact, but adorned with new features, perhaps a faint shell or ring of stars around its outskirts, formed from the remnants of the smaller galaxy's disk. We see hints of this in our own Milky Way. Our galaxy is surrounded by halo stars and thin streams that arc high above the disk, relics of dwarf galaxies and star clusters the Milky Way devoured in the past. These stellar streams are the ghosts of long-ago mergers, stretched out along the paths their original galaxies once took. Galactic collisions can produce wholly new galactic forms. A direct, head-on plunge of a small galaxy through the center of a larger one can send waves rippling through the larger galaxy's disk. In what's known as a ring galaxy, the impact triggers an outward-moving ring of stars and gas. The Cartwheel Galaxy is a dramatic example. It sports a bright inner ring and a larger diffuse outer ring, expanding outward like cosmic ripples after a stone drops in water. Those rings are not solid objects, but expansive waves of star formation, marking the front where the collision's energy is sweeping through the galaxy's disk. In other cases, collisions can puff up a galaxy into a diffuse ellipsoid. Two spirals of comparable size, when merged, might lose their orderly disks and form a big blob of stars, an elliptical galaxy. Around some ellipticals, astronomers see faint arc-like shells of stars. These are likely the vestiges of smaller galaxies that were swallowed, each shell a layer of stars left behind as the smaller galaxy's remnants adjusted into the new system. It's as if the big galaxy took a bite, and the ripple of that meal froze in place around it. These sculptural effects are often transient on cosmic timescales. A tidal tail may persist for a few 100 million years, but eventually the stars in it either disperse into space or fall back into the merged galaxy. Tidal bridges may get absorbed fairly quickly, melding into the bodies of the galaxies they connected. Rings gradually spread out and fade as their stars evolve and the wave dissipates. Shells become diffuse and hard to detect as stars move on. In time, the galaxy settles into a new equilibrium, and the dramatic distortions smooth out. But for those epochs when they exist, these features can dramatically alter a galaxy's appearance and stimulate further changes. The inflow of gas along a tidal tail can feed central starbursts or even awaken a galaxy's central black hole, lighting up an active nucleus. The new stars, born in collision-driven clumps, will live out their lives and enrich the galaxy with heavy elements when they die. Every bridge, tail, ring, or shell is a chapter in a galaxy's story. Looking at a peculiar galaxy shape, we can often infer that a collision did this. It's a bit like seeing footprints and knowing two creatures tussled here long ago. The universe is full of these clues. The strangely warped disk of one galaxy hints at a past encounter. The double nucleus of another indicates two cores mid-merger. The chain of star clusters trailing behind a galaxy points to a companion that has now vanished. Through these signs, we understand that collisions are not random wreckings, but creative acts as well. They redistribute matter and gas, sowing the seeds for new cosmic structures. In the aftermath of a collision, the stage is set for new stories. Perhaps a tidal tail will condense into a dwarf galaxy on its own, a kind of offspring of the collision. Or maybe the collision will trigger a wave of starbirth that seeds the galaxy with fresh young stars. In all cases, cosmic encounters leave an imprint that shapes the future evolution of galaxies. As we have seen, collisions and close encounters can tear apart and rebuild the cosmos on grand scales, forging new structures and mixing stellar populations. Yet out of this apparent chaos comes order, the next generation of stars, the next configuration of galaxies, and the ingredients for future planets. In our final chapter, we reflect on these cycles of cosmic destruction and creation, and how the violence of collisions may be crucial for the existence of things like us. The impacts and mergers of the past are, in a sense, the progenitors of future worlds. Throughout this journey, a pattern has emerged. Cosmic destruction often leads to creation. Colliding galaxies trigger starbursts that fill space with new stars. Merging black holes and neutron stars send out elements and energy that enrich the cosmos. Even at smaller scales, the chaos of star clusters can result in the birth of blue straggler stars, giving old regions a renewed sparkle. It seems that the universe has a way of reinventing itself through violence. Each collision shuffles the cosmic deck, mixing gases and stars into new configurations. In the wreckage of a galactic smash-up, there can be fuel for the next generation of stars and planets. Over cosmic timescales, this cycle of collision and renewal is essential to the universe's evolution. Without it, the cosmos would likely be a far more monotonous place, perhaps filled with many smaller, stagnant galaxies and fewer heavy elements for building planets and life. Indeed, we owe our existence to the residue of cosmic upheavals. The atoms in our bodies were forged in stellar furnaces and violent explosions. Many of the heavier elements like gold or uranium were created in the cataclysms of merging neutron stars or supernova. Our Sun is a second or third generation star, born from a nebula enriched by those earlier stars' scattered contents. That nebula may have been jostled into collapsing by some long ago disturbance, perhaps the shockwave of a nearby supernova or the tidal influence of passing stars. In a very real sense, the formation of our solar system was one small note in the grand symphony of cosmic encounters. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were brewed in stars and spread through space by events that, directly or indirectly, trace back to collisions or close encounters in the past. We find ourselves in the golden aftermath of countless explosions and mergers. The Milky Way's majestic spiral is built from collisions of smaller galaxies, its clouds seeded with the materials to make terrestrial planets and living organisms. Collisions have helped stir and redistribute these ingredients. They are not gentle processes. If you could watch and fast forward, galaxies coalescing would look like chaos. But given eons to settle, that chaos becomes the orderly grandeur of a mature galaxy with stable orbits and calm starry skies, a cradle where life can develop. It's humbling to realize that the serene night sky we know is a product of innumerable past upheavals. The universe had to be violent in order to become habitable. This realization brings us to a profound and wistful question. If the universe is so vast, dynamic, and generative, filled with billions of galaxies and untold trillions of planets born from these cosmic cycles, where is the evidence of other life? Space, as far as our instruments can detect, is eerily silent. We see no undeniable signs of alien civilizations, no radio beacons or galaxy-spanning empires. Our own planet is living proof that the ingredients scattered by cosmic events can assemble into thinking beings, yet we've heard no echo of other minds in the darkness. This conundrum is often referred to as the Fermi paradox, the contradiction between the high probability of life elsewhere and the lack of contact with anyone else. With all those stars and all those opportunities forged in cosmic crucibles, one might expect a universe teeming with life and intelligence. So one can't help but wonder, where are all the aliens? It is a question that hangs gently in the air as we conclude our exploration. We've seen how the cosmos, through collisions and creativity, constantly makes and remakes itself, setting the stage for new beginnings. Perhaps life is one of those precious outcomes, rare, fragile, and requiring just the right circumstances born of cosmic fortune. Or perhaps life is common, but the galaxy is simply too vast and too young for us to have met our neighbours yet. As we drift off under the starry sky, the myriad points of light above represent both the turbulent history of the universe and the hope of connections yet to be made. Maybe, somewhere out there in the quiet dark, other eyes are turned toward the sky, pondering the same mystery. In the tranquil silence of space, the question remains open, inviting us to seek answers among the stars. In this enormous, ever-changing universe, are we truly alone? Now, as our cosmic journey continues, we drift deeper into the quiet vastness where even the most serene night can be shattered by celestial violence. In the darkness between the stars, a rare and spectacular event unfolds. Two stars meet face to face. Normally, stars wander alone, with unimaginable distances separating them. But on extraordinary occasions, their lonely paths intersect, and when stars collide, the universe briefly ignites in a brilliant, transient blaze. Such stellar collisions are exceedingly uncommon, yet they do happen. In 2002, for instance, the star 5838 Monocerotis suddenly brightened and bloomed into a peculiar nebula. Astronomers believe this luminous outburst was caused by a pair of stars merging into one. Another dramatic case was recorded in 2008. An eclipsing binary in Scorpius, two closely orbiting stars, spiraled together and coalesced. The event, known as V1309 Scorpii, flared as a luminous red nova, a crimson stellar explosion signaling the moment of union. These luminous red novae are relatively gentle by supernova standards. Their reddish glow can linger for weeks or months. but they are unmistakable fingerprints of stellar mergers. Astronomers estimate such mergers are rare, perhaps only a handful per century in a galaxy like our Milky Way, making each one a precious cosmic spectacle. Indeed, only a few luminous red novae have been documented in our galaxy over the past 100 years, underscoring how special each event is. Whenever one is recorded, it provides direct, dramatic evidence of stars coming together in a cosmic union. When two stars collide, they may fling material into space, creating glowing shells of gas and dust, or they may completely meld into a single, more massive star. In either case, the aftermath can be picturesque. Imagine Gossamer Nebula expanding outward like blossoming cosmic flowers, enriched by elements dredged up from deep within the stars. Such stellar debris, lit by the heat of the collision, can form ephemeral clouds that gradually dissipate into the surrounding space. The merged star, if one results, may burn brighter and hotter, rejuvenated by the fresh infusion of fuel from its former companion. In ancient star clusters, scientists see indirect evidence of bygone collisions. There, amidst populations of old, red stars, they find enigmatic, blue-hot stars that look younger than they should be. These stellar oddities, called blue stragglers, likely formed when two older stars merged and rejuvenated into a hotter, bluer star. Calculations of collision rates in dense clusters align with the numbers of blue stragglers observed, suggesting that stellar collisions, essentially stellar cannibalism, are partly responsible for these youthful stars among the elders. It is a quiet testament that even in the crowded hives of globular clusters, stars sometimes meet and exchange their solitude for a violent embrace. For most stars, a direct collision never happens. Space is simply too vast. Our Sun, for example, will likely roam the galaxy for eons without ever colliding with another star. Yet some stars are born on a collision course from the start. Two stars bound by gravity in a binary system that will gradually tighten. What begins as a stable duet can turn into a fatal dance as energy leaks from their orbit through tidal forces and gravitational radiation. As their separation shrinks, they whirl around each other ever faster, like ice skaters pulling in their arms, until eventually they merge in a final cataclysm. This long, slow spiral toward an ultimate union is the hidden saga of many binary stars. In fact, decades before we could directly sense gravitational waves, nature provided a clue. A neutron star, binary, discovered in 1974, was observed to be slowly spiraling inward at exactly the rate general relativity predicted. By timing the pulsar's radio flashes over many years, astronomers saw the orbit shrinking ever so slightly, a gradual decay in perfect agreement with Einstein's theory. This was the first indirect proof that gravitational waves were real and were siphoning energy from the system, dooming the stars to eventually collide. Though that ultimate merger lies some 300 million years in the future, this observation confirmed how relentless and inevitable the process is. For binary stars, composed of more ordinary stars, say two sun-like stars, the path to collision might follow a different kind of cosmic choreography. Often, as one star ages and expands into a red giant, it engulfs its companion in a swirling common envelope of gas. This turbulent phase drains orbital energy rapidly, causing the two stellar cores to spiral together. The envelope of gas may be thrown off entirely in the ensuing chaos, drifting away as a glowing nebula, while the two stars inside coalesce. The result can be either a single new star or a binary remnant that's much tighter than before. Either way, what began as a gentle orbital waltz can end in a dramatic final clasp. As the binary stars tighten their embrace, the climax can be spectacular. Some mergers produce titanic explosions that briefly rival the brilliance of millions of suns. In other cases, the two stars quietly become one, with only a burst of newfound brightness to announce their union. Consider two white dwarf stars, Earth-sized stellar embers, slowly spiraling after eons together. If their combined mass is great enough, their merger can ignite a runaway thermonuclear explosion. Suddenly, a supernova erupts, obliterating the stars in a ferocious blaze of light. These collisions are thought to be one pathway behind Type 1, a supernovae, the brilliant stellar explosions often used as cosmic mileposts. Simulations suggest that white dwarf collisions could indeed trigger such supernovae, though perhaps only a tiny fraction of all Type Ia events come from this route. Still, the principle stands. A fatal rendezvous between two compact stars can unleash one of the most luminous fireworks in the universe. Not all stellar smash-ups completely destroy the participants. There is a whole menagerie of stellar explosions, and some are oddly subtle. Astronomers have identified a subclass of supernova-like events called Type IAX supernovae, less energetic blasts in which the star isn't entirely obliterated. One hypothesis is that these come from white dwarf mergers that only partially detonate. Recently, a fascinating remnant in our galaxy provided a clue. The nebula Per-30, an expanding cloud devoid of hydrogen and helium, but rich in sulfur and argon, matches the predicted remains of two white dwarfs colliding. In this case, the merger likely led to a fizzling kind of supernova. Powerful, yet not enough to completely annihilate the merged star. What makes this discovery even more remarkable is its tie to human history. The size of Per-30 and the speed at which it is expanding suggest the explosive collision occurred around the year 1181 CE. Chinese and Japanese astronomers at that time documented a very bright guest star that suddenly appeared in the constellation Cassiopeia and lingered for about 6 months before fading. It is awe-inspiring to realize that medieval skywatchers may have unwittingly witnessed the glow of that cosmic collision, a stellar merger lit up in Earth's sky nearly a millennium ago. When a star collision-triggered supernova lights up, it briefly outshines its entire galaxy. For weeks or months, that transient beacon can be visible across millions of light-years. In that searing flash, the fabric of the star is unmade, and its guts are scattered into space. All the elements once forged in the star's core, carbon, oxygen, neon, and more, are flung into the galaxy to mix with interstellar gas. These supernova sparks are not just destructive, they are creative as well. The ejected material seeds the cosmos with the ingredients for new stars and planets. In fact, the iron in your blood and the calcium in your bones were forged in ancient stellar explosions. But there are cosmic collisions even more exotic than stars blowing themselves apart. Some stars end their lives as ultra-dense remnants, neutron stars, which pack a sun's mass into a sphere the size of a city, or black holes, the even more extreme gravitational husks of massive stars. These dark, compact objects often travel in pairs as binaries, leftovers of stellar evolution bound together in orbit. If two neutron stars are locked together, they too will inevitably spiral inward and merge, and their collision unleashes one of nature's most astonishing spectacles. When neutron stars collide, the violence is almost beyond imagining. In that moment, densities and energies reach extremes that cause atomic nuclei to shatter and new elements to form. Astrophysicists got their first detailed glimpse of such an event in 2017. On August 17th of that year, gravitational wave observatories on Earth felt a subtle tremor in spacetime, the signal of two neutron stars spiraling together. Seconds later, a burst of gamma rays was detected, the hallmark of a short gamma ray burst, long suspected to occur when neutron stars merge. Telescopes soon caught sight of a kilonova at the collision's location, a cosmic fireball that glowed intense blue for days, then gradually faded to red, just as models had predicted. Within that fading glow, scientists identified signatures of freshly forged matter, an enormous abundance of heavy elements that had never been seen forming in real time before. Colliding neutron stars, it turns out, manufacture precious metals like gold and platinum by the Earth mass, along with many other elements heavier than iron. It was a stunning confirmation that in these cosmic smash-ups, the universe forges some of its most treasured ingredients. For a while, this discovery also deepened a mystery. The heaviest elements, gold, platinum, uranium, clearly can be made in neutron star mergers, but the observed merger rate seemed too low to account for all the gold in the universe. In all the years since 2017, no comparable event has been observed, highlighting how rare and fleeting these collisions appear to be. Yet thanks to new observations, including surprises from the James Webb Space Telescope, astronomers now suspect that neutron star mergers may be more common in the universe than we have directly witnessed. If so, these events could indeed be a major factory of heavy elements, seeding galaxies with precious metals over cosmic time. Even more silent and mysterious are collisions involving black holes. Imagine two black holes, invisible, yet each containing several times the Sun's mass, locked in a tightening orbit. As they draw closer, orbiting hundreds of times per second, they stir the fabric of spacetime and radiate ever stronger gravitational waves. In the final moment, the two black holes collide and merge into one. No light escapes that event, but a tremendous burst of energy ripples outward as gravitational waves, a brief vibration of the universe itself. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded, for the first time, the telltale tremor of spacetime from a black hole merger. Two black holes, roughly 36 and 29 times the Sun's mass, had coalesced in a galaxy about 1.3 billion light-years from Earth. During that merger, about 3 suns' worth of mass was converted into pure energy in the form of gravitational waves, most of it in the final fraction of a second, unleashing a peak power output that briefly exceeded the luminosity of all the stars in the observable universe. The signal that reached Earth was a faint chirp in LIGO's detectors. Yet from that whisper, scientists decoded the death spiral and collision of two black holes, confirming a major prediction of Einstein's theory. Since that first detection, scientists have eavesdropped on dozens of black hole mergers. Each event is like hearing a distant cosmic bell tolling in the darkness. These observations have revealed black holes merging at various masses and spins, sometimes in unexpected ways. In 2023, detectors picked up a record-shattering collision. Two black holes of about 103 and 137 solar masses spiraled together and formed a single black hole, roughly 250 times the mass of our Sun. This was the most massive black hole merger ever observed, and it forced astronomers to rethink how such giant black holes come to exist. The merging black holes were so large that they likely were products of earlier mergers themselves. By the time their gravitational waves washed over Earth, the event's fury had dwindled to a tiny ripple, but it told a profound story. Even black holes can have family trees, growing bigger through successive generations of collisions. It's poetic to think that we have never seen these black hole collisions with our eyes, and likely never will. But we have detected their effects by feeling the shape of space-time quiver. As one scientist noted, these are the most violent events we can observe in the universe. Yet when their signals reach Earth, they become the weakest phenomena we can measure. A collision that releases more energy in an instant than all the stars in the cosmos combined still arrives as nothing more than a whisper, stretching and squeezing space by less than a proton's width. Our instruments must be extraordinarily sensitive and quiet to catch such murmurs of cosmic violence. Through gravitational wave astronomy, the universe has revealed a new side of itself. Before, we observed the cosmos only through light. Now we can also hear it, sensing the subtle ripples of space-time directly. This new sense allows us to witness cosmic events that would otherwise be hidden, like black holes merging in complete darkness. It is as if we had been watching a grand cosmic ballet in silence, and have only now gained the ability to hear the music. Each gravitational wave detection is like a brief note in that symphony, a distinctive chirp, carrying information about cataclysms we could never perceive with conventional telescopes. After witnessing all these dramatic unions, stars colliding, white dwarfs igniting, neutron stars and black holes merging, one might feel humbled by the cosmos's capacity for both creation and destruction. Yet between these rare cataclysms, the universe is overwhelmingly tranquil. Eons pass quietly as stars shine, and galaxies drift through the dark. It's in those long interludes of peace that we can reflect on the significance of the violent events we've observed. Each collision, while catastrophic on a local scale, contributes to the grand story of the cosmos, dispersing elements, altering the destinies of stars, and subtly shaping the evolution of galaxies. In the stillness that follows a star's explosive end, the cosmos slowly recovers its breath. The blinding flash fades, and the echoes of the blast dissipate into silence. The heavy atoms forged in a neutron-star merger or supernova drift through space, perhaps one day to become parts of new stars, new planets, or even new life. Out of cosmic violence comes cosmic creation, and out of the noise comes a profound quiet once again. Having explored collisions on the scale of stars, we now lift our gaze to a far larger stage. Even galaxies themselves can collide and merge in slow-motion dances spanning billions of years. In fact, our own Milky Way is on a collision course with the neighbouring Andromeda galaxy, expected to begin its grand union about 4 to 5 billion years from now. When that happens, the vast distances between individual stars mean that few, if any, stars will actually collide head-on. Instead, the two galaxies will gradually intermingle and distort each other's shapes, flinging some stars into new orbits. Gas clouds will slam together and ignite bursts of star formation before the galaxies ultimately coalesce into a larger, combined system. It is a majestic process on a scale far beyond any single star collision. Our journey is about to venture onto that larger stage of galactic collisions. But for now, we pause in the quiet after the stellar storms we've witnessed, letting the enormity of these cosmic encounters sink in. The stage will soon grow larger, the actors more numerous, yet the underlying story of gravity's grand design continues. When we return, we will step into this vast arena of colliding galaxies and watch the next chapter of the universe's unfolding drama. In the silent depths of space, nothing is truly still. Galaxies that seem isolated and serene are in fact drifting, drawn gently by gravity's inexorable pull. Across millions and billions of years, these great star cities travel through the cosmic dark, their paths shaped by the gravitational whispers of other galaxies. Sooner or later, their wandering leads them into a slow embrace. It is the fate of many galaxies to meet and merge, to collide and become something new, given enough time. From our perspective, within a single human lifetime, galaxies appear eternal and unchanging. A galaxy's lifespan is measured in eons, far beyond our scale, and change unfolds so gradually that we cannot witness it directly. Yet the universe operates on a far grander clock, and over immense spans of time, even these enormous islands of stars cannot escape interaction. In distant reaches of the cosmos, astronomers have captured glimpses of galactic pairs caught in the act of merging. Through our telescopes, we see colliding galaxies tangled together by their mutual attraction, sometimes forming spectacular shapes as they slowly combine. Long, wispy streams of stars get flung out like cosmic ribbons, arcing into space as two galaxies pull on each other. Bright knots of newborn stars light up where the galaxy's gas and dust crash together and intermingle. Such scenes, frozen in images from space observatories, remind us that collisions are a natural part of galactic life. Indeed, our own galaxy carries the quiet evidence of past encounters. The Milky Way has gently absorbed smaller galaxies over its lifetime, adding their stars to our galactic family. Even now, remnants of these long-ago mergers can be found. Great loops and streams of stars in odd trajectories, the faint traces of dwarf galaxies being torn apart and assimilated into the Milky Way's halo. One such stellar stream, the ghostly remains of a small galaxy, wraps around us like a gossamer ribbon, silent testimony that our Milky Way is not a solitary island, but a gathering of many souls. These cosmic mergers are not sudden catastrophes, but slow dances, unfolding over hundreds of millions or billions of years. Gravity choreographs their steps, drawing two star systems gradually into one another's influence. At first, they may merely brush past, each warping the other's shape with tidal forces that stretch and distort their spiral arms. But if they are bound by gravity's embrace, they will inevitably circle closer, like dancers drawn into a tightening spiral, until eventually they join as one. Galaxies on a collision course move with a measured grace that belies the violence of their fate. The vast distances between individual stars mean that when two galaxies finally meet, their stars usually slip by one another rather than smashing together. The scale is so immense that even as galactic disks collide, the chance of any two stars crashing head-on is vanishingly small. They pass like grains of sand in a gentle stream, mostly untouched by direct impact. And yet, the overall structure of each galaxy is transformed by the encounter. Their once majestic spiral arms may become tangled and stretched out behind them. Clouds of interstellar gas and dust are jostled and compressed amid the gravitational turmoil. New patterns of stars and nebulae begin to form from the chaos. Over time, two separate galaxies gradually become one larger, reshaped system, a cosmic union that bears the memory of its origin in faint stellar streams and merged cores. In the fullness of cosmic time, collisions like these are inevitable and, in fact, relatively common. Every large galaxy we see today has likely experienced multiple mergers throughout its existence. The universe itself was built on such unions. In the distant young cosmos, smaller protogalaxies continually collided and coalesced to form larger ones, generation by generation. In crowded clusters of galaxies, these interactions happen more frequently. Galaxies may collide and merge repeatedly, creating giant elliptical galaxies at cluster centers that are the product of dozens of past collisions. Our own Milky Way resides in a quieter neighborhood, but even here, in the silent darkness of intergalactic space, it is slowly heading toward a grand encounter of its own. far beyond the horizon of human time. An immense cosmic rendezvous awaits our galaxy. No corner of the universe remains truly isolated forever, and in several billion years, the Milky Way will meet its great companion and change forever. Across the vastness of space, two enormous spiral galaxies are drawing ever nearer, bound by a fate set in motion eons ago. One of them is our own Milky Way, and the other is the Andromeda Galaxy, a majestic spiral that currently lies just beyond our galactic neighborhood. If you gaze up on a clear, dark night and know exactly where to look, you can spot Andromeda as a faint, smudged glow in the sky. It does not look particularly large or impressive to the naked eye at present, just a misty patch of light, easily overlooked. Yet that dim patch is the combined glow of 1 trillion distant stars, and it is hurtling toward us. With each passing second, Andromeda comes slightly closer, drawn by the gravity that binds our galaxies together in a slow but inevitable dance. The approaching galaxy is still millions of light years away, so far that its movement is imperceptible on human timescales. But over the course of billions of years, those light years will shrink. Andromeda edges closer at a speed of about 110 kilometers every second, a colossal velocity, though in the emptiness of space, it seems almost gentle. At that rate, which would cover the span of continents here on Earth, in the blink of an eye, the gap between our galaxies is slowly closing. What is now a tiny blur will grow gradually brighter and larger in the sky of the far future. If some distant descendants of humanity, or perhaps other beings entirely, were alive billions of years from now, they would see Andromeda transform from a faint cloud into a magnificent swirl of stars spread across the heavens. Night after night, over millennia, the hazy form would expand and brighten until it dominates the cosmic panorama. This spectacular transformation in the sky would unfold so slowly that countless generations could live and die under an ever-changing tapestry of stars. Eventually, roughly 4 billion years from now, according to current estimates, Andromeda and the Milky Way will begin to truly feel each other's grasp. Long before they physically collide, their immense halos of tenuous gas and dark matter will intermingle. Out in the far reaches, where each galaxy's influence extends, stray hydrogen atoms and the thin shroud of invisible dark matter will brush together, announcing the first whispers of an encounter. Then comes the moment when the two galaxies make their first close pass. This will not be a sudden crash, but a drawn-out gravitational entanglement. Andromeda's bright spiral disk will begin to distort the shape of our Milky Way, and vice versa. From within our galaxy, the night sky would undergo breathtaking changes. A luminous band of foreign stars, the heart of Andromeda, might sweep across the darkness, far larger than our current Milky Way band that stretches overhead on summer nights. The approaching galaxy's core could shine like a second swarm of stars rising at dusk, an island of light growing every century. As Andromeda swoops in for this initial encounter, the two galaxies will likely miss a direct hit in the first pass. Instead, they might sideswipe one another. Such a glancing blow will dramatically warp both galaxies. Andromeda's spiral arms may tangle with our own, perhaps ripping streamers of stars and gas from each galaxy and flinging them outward. Our Milky Way might send ripples through Andromeda's disk, while Andromeda's gravity yanks stars from the Milky Way's outskirts. In the sky, observers would behold breathtaking sights, great arcs of stars drawn out into space, and swirling patterns forming as the galaxies intermix. The stars are so far apart that they will weave through this chaos largely unharmed. Our solar system could be carried along as the Milky Way's shape is disturbed. Perhaps we would find ourselves in a completely different part of the galaxy after the pass. It is even possible that the Sun and its planets might be tossed into a higher orbit around the merging galaxies, or cast adrift into intergalactic space. But for the most part, stars will simply regroup under the altered gravitational landscape as the two galaxies begin their dance anew. After that first dramatic flyby, Andromeda will not simply disappear into the distance. The intimate gravitational embrace ensures the galaxies are now bound, like two dancers who have brushed past and caught hold of each other. Andromeda will slow down relative to the Milky Way as they trade energy through tidal forces, and eventually it will be drawn back for another encounter. The two galaxies, now intertwined by gravity, will oscillate around their common center. After perhaps a few billion years of an elaborate orbital ballet, they will meet again for a second close approach, then perhaps another. Each encounter further melds their stars, gas, and dark matter together. Bit by bit, pass by pass, the distinct identities of Milky Way and Andromeda begin to blur. Their beautiful spiral arms, once so well defined, become increasingly disordered with each meeting. They may fling out long tidal tails, enormous stellar streamers that extend for hundreds of thousands of light years, marking the space through which they have come. In time, these two mighty galaxies will coalesce entirely, merging their cores and forming a single, much larger galaxy. When the Milky Way and Andromeda finally merge into one, the result will be a transformed galactic home. Astronomers predict that the merged galaxy could be an elliptical galaxy, a big, football-shaped collection of stars, without the elegant spiral patterns we are used to. The stars from both galaxies will settle into new orbits, creating a more random, blended distribution rather than orderly spiral arms. The night sky in that far epoch would no longer show the arching band of the Milky Way's disk as we know it, because the disk may be disrupted and dissolved. Instead, the sky would glow with a more diffuse halo of stars surrounding a bright central core, the mark of an elliptical galaxy. This combined galaxy might possess a new name, but it will essentially be the offspring of the Milky Way and Andromeda, carrying pieces of each within its stellar population. And while the merging process is dramatic, it is also a new beginning. The union of these two great galaxies will spark changes that echo for ages to come, from bursts of star formation to the eventual settling of a new cosmic city of stars. In the aftermath of this titanic merger, a smaller neighbor, the Triangulum Galaxy, may find its fate intertwined as well. Initially, this diminutive galaxy could remain separate, orbiting the newly formed giant from afar like a satellite. Over time, however, gravity's pull would draw Triangulum inward toward the larger mass. It too would eventually merge, adding its stars to the growing galactic realm. As tens of billions of years pass, what once was a loose gathering of separate galaxies will condense into a single colossal galaxy. This final megagalaxy would contain the stars that long ago belonged to Andromeda, the Milky Way, Triangulum, and numerous smaller companions. All of those stars would be united in one grand stellar assembly, the completed portrait of our local group's destiny. It is a quiet finale for a once separated family of galaxies, now merged into one. It is humbling to imagine this future collision, because by the time it happens, the Earth as we know it may no longer be around to witness the spectacle. In roughly 4 to 5 billion years, when the first act of this galactic dance unfolds, our Sun will itself be nearing the end of its life. The Sun is expected to swell into a red giant star around that distant era, likely scorching and swallowing the inner planets, including Earth, or at the very least, rendering our homeworld uninhabitable long before the galaxies fully merge. So the grand cosmic dance of the Milky Way and Andromeda may play out to an empty terrestrial theatre. If any life forms observe the sky of that distant time, they might not be human at all, but perhaps new beings evolved on worlds not yet formed, or descendants of humanity who have ventured to other stars. Whoever and wherever the watchers are, they would see a truly awe-inspiring slow-motion collision, a sky first spangled with the approach of a sister galaxy, then ablaze with the blended starlight of two galaxies becoming one. This cosmic spectacle would unfold in slow grandeur, spanning billions of years, yet it will fundamentally reshape our galactic neighborhood forever. Long after the final coalescence, the merged galaxy will carry on through the cosmos, a lasting testament to the incredible journey that brought two starry realms together. Every component of a galaxy responds to a merger in its own way, and the most immediately visible participants are the stars. When galaxies unite, billions of stars from each swirl together under the influence of a new combined gravity. Individual stars, however, are so tiny compared to the gulfs between them that they almost never collide directly. Two galaxies can interpenetrate like overlapping clouds of fireflies, with their stellar points of light simply gliding past one another. From a star's perspective, the merger is mostly a grand shift in gravitational scenery, rather than a series of collisions. Paths that were once steady orbits around a galactic center become wildly altered as the galaxies draw together. The combined gravitational forces disrupt the old order, flinging many stars into new trajectories. Some stars may be tossed far out into the expanding halo of the merged galaxy, becoming lonely wanderers on the outskirts. A few might even be slingshotted to such high speeds that they escape entirely, turning into intergalactic drifters, free of any galaxy. Most, however, will remain bound to the new system, eventually settling into orbits around the merged galactic core. As the galaxy's stars blend together, the graceful order of each original galaxy begins to break down. A spiral galaxy's familiar structure relies on most stars following a rotating disk pattern. In a major merger, that orderly rotation is disrupted. Stars that once travelled in neat flat circles around the galactic center are sent onto new paths that tilt and loop in all directions. Over time, the colliding galaxies lose their defined spiral arms and flat disk shape, evolving into a more rounded swarm of stars. What emerges is often an elliptical-shaped galaxy, essentially a puffed-up ellipsoid of stars, moving in random orbits, rather than a thin disk. This is why when two galaxies of similar size collide, the end product is typically an elliptical galaxy. The stars from both progenitors become one merged population, scrambled and resettled into a new configuration. The final galaxy bears little trace of the original spiral's patterns, instead shining with a diffuse, centralized glow of countless stars spread in all directions. While the stars behave like test particles swirling in a gravitational dance, the gas within galaxies experiences a far more turbulent fate. Gas clouds, unlike stars, do collide and interact directly during a merger. Each galaxy contains vast regions of hydrogen gas and interstellar dust, the raw material for new stars. When two galaxies interpenetrate, their gas reservoirs crash together like colliding weather fronts. Enormous shockwaves ripple through the interstellar medium as these gaseous masses converge. The impact compresses the clouds dramatically, and under this pressure, many clouds collapse and fragment. All this turmoil kicks star formation into high gear. Regions that were once calm begin birthing stars at a furious rate, far above the normal pace. Astronomers call this phenomenon a starburst, an intense flare-up of star birth triggered by the merger. Throughout the merging galaxies, new clusters of massive, hot stars ignite, pouring brilliant blue light and energizing the surrounding nebulae. Entire swaths of the colliding galaxies light up with this stellar fire, a cosmic fireworks show signifying the creation of countless new suns. Not all of the gas churned up by the collision ends up forming new stars. A significant portion of the disturbed gas, having lost much of its previous orbital energy, begins to flow inward towards the center of the merging galaxies. In the chaos of the collision, streams of gas are funneled deep into the galactic core, as if the violence of the encounter herds matter into the nucleus. There, this influx of material encounters the supermassive black holes that reside in each galactic heart. Normally, these central black holes might lie quiet and invisible against the starlight, but a merger can awaken them. As gas swirls into the combined center, it forms a hot, rotating disk around the black holes and heats up to extreme temperatures. The once dormant black holes are suddenly fed with abundant fuel, causing them to roar to life. They begin devouring the inflowing gas and, in the process, release tremendous energy. For a time, the center of the merging galaxy may blaze as an active galactic nucleus, perhaps even a quasar, shining brilliantly as matter pours into the black hole. This stage of the merger can transform an otherwise quiet galactic core into one of the brightest beacons in the universe. Thus, the behavior of gas during a merger is dramatic, not only in birthing new stars, but also in feeding the monster at a galaxy's core, fundamentally altering the galaxy's energy output and appearance. Amid all this chaos, there is also the matter we cannot see, dark matter. Every galaxy is thought to be surrounded by a vast halo of this invisible form of mass, which actually outweighs all the visible stars. When two galaxies merge, their dark matter halos pass through each other, almost like ghosts merging in the night. Dark matter particles do not collide and crash like gas clouds. They interact only through gravity's pull. So as the galaxies come together, the dark halos simply overlap and begin to form a single combined halo. Some dark matter particles from one galaxy fly straight through the other galaxy's core and out the far side, slowing only gradually as the gravitational pull of the whole merging system draws them back. Over time, the dark matter from both galaxies settles into a larger, blended halo that encompasses the new, merged galaxy. This enlarged halo becomes the gravitational scaffold holding the merged galaxy together. Though we cannot see the dark matter, its presence is crucial. It shapes the final structure of the galaxy and limits how far the stars and gas can wander. In the end, the dark matter's silent rearrangement provides the foundation for the cosmic city that emerges from the merger. Bringing together all these elements, stars, gas, and dark matter, a galactic merger is a transformative event. Through their gravitational interaction, two separate galaxies are reforged into a single entity. What starts as chaos eventually settles into a new order. In the aftermath of the merger, the resulting galaxy is typically larger and dynamically different from its parents. The once distinct communities of stars have become one, all swirling under a common gravitational field. If the collision was violent, and most of the gas was either consumed in starbursts or funneled into black holes, the new galaxy may have exhausted much of its star-forming fuel. Such a galaxy could shine primarily with the combined light of older stars, a vast city of ancient suns now living together, Not all mergers end in exhaustion. Sometimes the cosmic union leaves behind numerous young star clusters and glowing nebulae, stellar nurseries lit by brilliant newborn stars born of the starburst. Either way, the galaxy that emerges is a bold statement of cosmic evolution, carrying the merged legacy of its predecessors. The shapes and structures that once defined the original galaxies are gone or greatly altered, yet nothing is truly lost. It has merely been rearranged into a new design. From upheaval, a new galaxy is born, bearing within it the story of the galaxies that came together. In time, this larger galaxy will continue its journey through space, perhaps destined to encounter other companions in the distant future. And so the grand cycle of cosmic growth through collisions will carry on. One of the most spectacular consequences of galactic collisions is the burst of new star formation that they often ignite. When two galaxies crash together, their cold gas clouds are jolted and compressed, and this upheaval can set off a celestial fireworks display of newborn stars. Astronomers refer to this phenomenon as a starburst, an aptly chosen term to describe a sudden, intense flurry of star birth. In an otherwise calm universe, a merging galaxy pair can blaze with dozens or even hundreds of brilliant star-forming regions, each shining like a cosmic bonfire. These hotspots of creation are the direct result of the collision's chaos, which forces gas that once drifted lazily through space to collide and condense into embryonic stars. Inside a starburst region, the scene is one of both beauty and frenzy. Massive stars are being born in great numbers, lighting up their birthplaces with an intense blue-white glow. Great billowing nebulae, vast clouds of gas and dust, become illuminated from within by clusters of these newborn stars. In the core of such a nebula, the burst of star formation can be so vigorous that it exhausts the local gas supply in a relatively short time, where a typical spiral galaxy might form only a few new stars in a year. A starburst galaxy can create hundreds in the same span. To an observer, parts of the merging galaxies would appear studded with unusually bright knots and patches. Each knot is like a city of young stars, densely packed and shining fiercely amid the cosmic turmoil. The combined light of countless hot, massive stars gives those regions a striking bluish hue, a telltale sign of recent star formation on a grand scale. Astronomers have witnessed such starburst fireworks in many interacting galaxies. A famous example is the antennae galaxies, a pair of colliding galaxies whose cosmic tussle has sparked a frenzy of star birth. In images of the antennae, bright clumpy regions are scattered throughout the merging galaxies, each marking where intense clusters of stars are forming. Those young clusters are teeming with massive stars that will live fast and die young. Indeed, in any starburst, the most massive newborn stars burn through their fuel in just a few million years, ending their lives as supernovae. So amid the light of creation, there also come explosions of destruction. Titanic supernova blasts pepper the starburst region as those short-lived stars reach the ends of their brief lives. Seen from afar, these stellar explosions would register only as tiny flashes in the galactic glow, but their effects are far-reaching. Shock waves from supernovae carve through the surrounding gas, stirring and heating it even further. Sometimes these shocks trigger additional rounds of star formation nearby. Other times they blow gas out of the region entirely, eventually quelling the starburst frenzy. Either way, the supernovae enrich the galaxy with heavy elements: the calcium in our bones, the iron in our blood, the oxygen we breathe, were all forged in such stars and dispersed by their explosive deaths. In this way, a starburst not only builds new stars, but also seeds its galaxy with the raw ingredients for future planets and perhaps future life. Starbursts are brilliant, but fleeting phases in a galaxy's life. They can burn themselves out in a matter of only tens or hundreds of millions of years, a blink of an eye in cosmic terms. After the fireworks fade, the galaxy is forever changed. Its reservoirs of cold gas may be largely depleted or heated, leaving the merged galaxy with far fewer resources to forge new stars in the future. What remains is a galaxy filled with the stellar handiwork of the burst. Countless young stars, many destined to age and fade in time, and star clusters now drifting throughout the galaxy. The once violent heart of the starburst grows quieter. In many cases, the aftermath of a major collision is a galaxy that has transitioned from a youthful, star-forming system into a more sedate, mature one. It shines mostly with the combined light of older generations of stars, now enriched by the heavier elements created during the frenzy. Thus, the cosmic celebration of light leaves behind a lasting legacy of new suns and enriched matter, setting the stage for whatever comes next. And while the visible fireworks eventually dwindle, another drama is unfolding invisibly at the galaxy's center. The slow dance of supermassive black holes drawing ever closer, preparing to merge in their own titanic union. In the heart of nearly every large galaxy lies a supermassive black hole, a gravitational titan millions or billions of times the mass of our Sun. When galaxies collide and merge, these central black holes are destined to meet as well. Initially, after the galaxy's stars and gas have coalesced into one system, the two black holes might roam within the chaotic core, each surrounded by its own cluster of stars. They drift through the aftermath of the collision, like quiet, dark sentinels. But slowly, inexorably, they are drawn toward each other by their immense gravity. Just as the galaxies themselves merged, so too must their central black holes, beginning a gravitational dance that will end in a profound union. At first, the two supermassive black holes orbit at a distance, circling the common center of mass of the new galaxy. Their presence is largely hidden. They emit no light of their own unless gas falls into them, and much of the time they lurk unseen amid the stellar hubbub of the crowded galactic core. Yet their gravity influences the orbits of nearby stars, gradually stealing energy from those stars and causing the black holes to spiral closer together. This process, known as dynamical friction, is slow but relentless. Over millions of years, the two invisible giants draw nearer, their orbit tightening step by step. As the black holes approach within a few light years of one another, they form a bound binary system, two dark masses locked in orbit. They circle in the darkness, orbited in turn by swarms of stars that are being gravitationally slingshotted away. In these later stages, the dance of the black holes speeds up. What was once a yearly orbit becomes a monthly orbit, then weekly, then by the final phases, they are whirling around each other many times per day. Despite their enormous mass, they now lie only a fraction of a light year apart, closer than some stars in a star cluster. There is no fanfare of visible light at this stage. From afar, one would still see nothing remarkable. But space-time itself begins to tremble from their motion. As the two black holes spiral inwards, they stir the fabric of space-time and send ripples outward. These ripples are gravitational waves, faint distortions in reality that race away at the speed of light. In the final centuries and years before the merger, the black holes are emitting an ever-increasing barrage of these waves. If we could somehow hear gravity, we would perceive a deep, rising tone as the black holes sweep closer and orbit faster. For now, such waves are imperceptible to our senses, and even the galaxies surrounding the event will not feel them in any tangible way. Yet, across the universe, the very structure of space is carrying the news of two giants on the verge of becoming one. In the last moments, the two black holes draw unimaginably close, moving at nearly the speed of light. They may orbit each other hundreds of times in the final few hours, a furious finale to their eons-long courtship. Then, finally, they merge. In that instant, an enormous amount of energy is released, not as a flash of light, but as a monumental burst of gravitational waves. For a brief moment, this merger radiates more power in gravitational energy than all the stars in the observable universe combined. The wavefront carries away a portion of the black hole's mass energy, ringing space-time like a colossal bell. Any advanced civilization with sensitive detectors, even billions of light-years away, would register this event as a faint yet distinctive tremor passing through the cosmos. When the cosmic quaking subsides, only a single, even more massive black hole remains where two once circled. This newly formed black hole may recoil slightly from the force of the merger, like a cannon firing, potentially moving it off-center for a time. But it will eventually settle near the center of the merged galaxy, becoming the gravitational anchor of the new system. In the aftermath, the black hole might briefly feast on whatever gas is nearby, producing a last glimmer of radiation. Soon, however, it likely lapses into quiescence, having consumed or flung away the material that once fueled its brilliance. The merging of supermassive black holes is the invisible climax of a galactic collision. It happens on a timescale long after the initial crash of stars and gas, perhaps hundreds of millions of years after the first mingling of the galaxies. By the time the black holes unite, the surrounding galaxy has already settled into its new form. There may no longer be bright starburst nebulae or spectacular tidal tails. Those have faded with time. But deep in the core, the final seal on the merger is set by this union of darkness. Two ancient singularities that once inhabited separate galaxies are now one. Though shrouded in mystery and darkness, the merger of the central black holes has profound implications. It completes the transformation of two galaxies into one, ensuring that even their most secret hearts are joined. The single colossal black hole now harbors the mass of both original black holes, and it can grow even larger if more matter drifts into its grasp. Such a leviathan could power an active galactic nucleus, or quasar, if given fresh fuel. Or it might remain a sleeping giant until disturbed again. In either case, it stands as a monument to the deep, time-drawn connection between the once separate galaxies. In our own local group of galaxies, this fate awaits the Milky Way and Andromeda. If our descendants are around in some far future, they might not see the black holes merge with their eyes, but perhaps they could detect the subtle ripples of space announcing the event. The merging black holes will silently sculpt the future of our night sky, as the unified Milky Way Andromeda galaxy, by then perhaps an enormous elliptical, settles into long-term stability. The great cosmic collision will thus end, not with a bang we can see, but with a tremendous distortion of space-time that only the universe itself can truly witness. Galactic collisions can produce some of the most arresting shapes in the universe. In the throes of their interactions, galaxies are often stretched and deformed, trailing long streamers of stars, or even forming peculiar rings of light. What begins as two orderly spirals can become an entwined, chaotic structure that defies the galaxy's original appearance. Over time, as the chaos settles, these distortions either disperse or give birth to entirely new galactic forms. In short, collisions turn cosmic order into creative disorder, sculpting new shapes from the remnants of the old. One common outcome of a close galactic encounter is the creation of tidal tails, immense elongated streams of stars, gas, and dust flung far out into space. As galaxies draw near and gravitational forces tug unevenly on them, stars from their outer regions can be pulled loose, escaping the confines of their original galaxy. These stars spill out to form arcing bridges or tails that connect the galaxies like celestial taffy being stretched. A striking example is seen in the antennae galaxies, where two merging galaxies have thrown out dual tails of stars extending for tens of thousands of light years, resembling the antennae of an insect. These tails are studded with bright young star clusters, sparkles along the thin, drawn-out lines of starlight. Tidal tails are ephemeral on cosmic timescales. They maintain their shape for a few 100 million years at most before dispersing, as their stars either fall back into the merged galaxy or drift away into intergalactic space. In some cases, clumps of gas and stars within a tidal tail can condense under their own gravity and form new dwarf galaxies, essentially miniature galaxies born as a byproduct of the collision. Thus, a galactic merger can spawn entirely new star systems, cast off as scraps from the main event. Eventually, though, most of the material in tidal tails either rains back down upon the remnant or is lost to the darkness between galaxies. Another striking structure born of specific galactic collisions is the ring galaxy. If a smaller galaxy passes directly through the center of a larger spiral galaxy's disk, it can send gravitational ripples outward, like a stone dropped in a pond. The result is an expanding ring of stars and gas. One of the most famous examples is the Cartwheel Galaxy, which displays a nearly perfect ring dotted with brilliant blue star clusters. This cosmic ring was likely generated when a smaller intruder galaxy pierced through the Cartwheel's heart, triggering a circular wave of star formation that spread outward. Ring galaxies are relatively rare and transient, slowly dissolving as the ring expands and breaks apart. But for a while they stand as cosmic bullseyes marking the scene of a dramatic collision. In the longer term, many collisions, especially between similarly sized galaxies, settle into more familiar, if less flamboyant, shapes, after the dust and tails have either fallen back in or drifted away. What remains is often an elliptical galaxy, where once there were neat spiral arms, the merged collection of stars forms a more amorphous blob of light. Elliptical galaxies, with their rounded, smooth profiles, are essentially the end products of repeated mergers and interactions. Their chaotic beginnings, full of tails, rings, and bursts of stars, eventually relax into a state of equilibrium, a big ball of stars with no clear pattern beyond a gentle gradient of brightness. It's a calmer appearance that belies the violent origin. Galactic collisions can also produce other oddities: warped disks, polar rings, double cores, and other irregular forms. Some galaxies that have only grazed each other may emerge with one spiral arm longer than the other, or with a bar of stars slicing through their center. The variety of outcomes is vast, depending on the angles, speeds, and sizes involved in the crash. Yet, despite the seeming chaos, there is a sort of cosmic artistry at work. Each collision writes a unique story in the stars, a story visible in the shapes we see long after the initial event. In gazing at peculiar galaxies, those with loops, tails, or rings, We are witnessing snapshots of cosmic evolution midstream. Given enough time, those dramatic features will either fade into the galactic body or detach and wander off. The ring will dissipate, the tails will thin out, and the galaxy will continue on in a new form, often more settled and featureless. The chaotic sculpting of the collision is thus temporary, but it provides a window into the dynamic lives of galaxies. Each loop and smear of stars is a lingering footprint of a cosmic encounter, evidence that such mergers have been reshaping galaxies since the universe's youth. Over the grand sweep of cosmic time, collisions have been fundamental to shaping the universe we see today. The first galaxies formed when smaller proto-galaxies merged. Larger structures grew by devouring smaller ones. In a real sense, cosmic collisions are the universe's way of growing and recycling. They drive the evolution of galaxies, triggering new generations of stars, redistributing gas and heavy elements, and building up ever larger cosmic structures. Without collisions, the cosmos would look very different. The majestic galaxies we admire in the night sky might never have attained their scale or richness. Reflecting on these colossal events, one realizes that destruction and creation in the universe are deeply intertwined. A galactic collision is violent and chaotic, yet out of that chaos comes renewal. Starbursts that forge fresh stars, black hole mergers that reshape the heart of galaxies, and rich tapestries of stellar material spread across space. The universe has a long history of such events. Billions of years before our sun was born, ancestral galaxies were already crashing together, seeding the cosmos with the elements that would one day make planets and people possible. The calcium in our bones and the iron in our blood likely owe their existence to supernovae in long-ago starbursts, perhaps triggered by those ancient collisions. In this way, our own existence is connected to galaxy collisions. The Milky Way itself is a product of countless mergers on various scales. Not only the upcoming grand merger with Andromeda, but also the absorption of many smaller galaxies in the past. The stars that surround us carry vestiges of those events. Some streams of stars in our galaxy today are remnants of smaller galaxies torn apart eons ago. We live in a cosmic ecosystem that has been nurtured and pruned by collisions. It's a humbling thought that the peaceful night sky we behold, with its steady stars and faint band of the Milky Way, is in fact the result of countless interactions and transformations. When we contemplate the Fermi paradox, the question of where the aliens are in a universe so vast, it's worth remembering the backdrop of cosmic change against which life might evolve. Galaxies collide on timescales immensely longer than a human civilization's, but their effects can be profound over billions of years. They can rearrange environments, spark waves of star and planet formation, and perhaps occasionally extinguish nascent biospheres with bursts of radiation. Life in the universe, if it is out there, must navigate a cosmos that is far from static. Civilizations might arise in tranquil epochs between cosmic fireworks, or look to the skies with awe as neighboring galaxies drift close. For now, humanity's perspective is limited. We are newcomers on the cosmic stage, only beginning to grasp these titanic processes. Our entire recorded history is but a heartbeat compared to the slow choreography of galaxies. Yet, through science and imagination, we can extend our view across time and space to witness these events in our mind's eye. We see that the universe is not a quiet, still place, but a dynamic, ever-changing tapestry. Collisions and mergers are among its grandest strokes, sometimes destructive, often creative, always transformative. As we look up at the night sky, we might try to sense the ancient and ongoing drama playing out beyond the stars we see. Every galaxy has a story written by interactions and collisions. Spirals that twirl gracefully now were perhaps shaped by past entanglements, and many will one day merge and change form. Our own galaxy's story is still unfolding. We know that far in the future, long after our sun has died, the Milky Way will complete its dance with Andromeda and become a different kind of galaxy. Whatever beings are there to see it, if any, will witness a night sky unlike our own, moulded by events we are only now coming to understand. In the end, the tale of galaxy collisions is a tale of change on the most stupendous scale. It reminds us that even the mightiest structures in the universe are not eternal islands, but travelers on intersecting paths. They meet, interact, and combine, driven by gravity's unyielding pull, contributing to an ever-evolving cosmic landscape. For us, contemplating these colossal interactions stretches our perspective beyond the confines of a human lifespan. It invites a sense of wonder and perhaps solace that even in what seems like destruction, the universe is crafting new beginnings. The grand heritage of starlight and substance we come from was forged in part by these very collisions. In the distant future, new worlds and stars will likewise be born from the remnants of today's galaxies. The cosmic story is still being written, and galactic collisions are among its most dramatic chapters, glorious, mysterious, and essential to the universe's endless creativity. The cosmic stage is far from peaceful. In the vastness of space, gravity gently tugs on everything, drawing distant objects inexorably closer over eons. Even in an almost empty universe, this subtle force ensures that nothing remains truly isolated forever. In time, stars drift nearer, galaxies approach one another, and colossal worlds cross paths, setting the scene for the universe's grand collisions. These cosmic encounters are not sudden, explosive crashes like a car accident, but rather slow, majestic dances unfolding over millions or even billions of years. When galaxies begin to meet, they respond to each other's gravitational embrace gradually and gracefully. Their shapes, often elegant spirals, start to distort, stretching out like taffy under an invisible pull. Over long spans of time, they swirl together, exchanging material and energy, and eventually merge to form a new, transformed galaxy. In the youthful universe, galaxies were smaller and more numerous, and interactions were far more frequent than today. Within a few 100 million years after the Big Bang, the very first stars gathered into tiny protogalaxies. These diminutive galactic building blocks swarmed and merged, combining their stars and gas to build larger galaxies step by step. Over billions of years, this gradual, hierarchical growth produced the giant galaxies we see in the present era. In this way, collisions have gradually built up the cosmos we know. The universe's grand architecture is the product of innumerable mergers and interactions. From small star clusters joining larger groups to entire galaxies coalescing into bigger ones. Without these unions, the rich tapestry of cosmic structure, spiral galaxies, giant ellipticals, and vast clusters of galaxies might never have come to be. Indeed, every galaxy we observe, including our own Milky Way, bears the marks of past collisions that helped shape it into its present form. Each collision writes a new chapter in cosmic evolution. A pair of galaxies drawn together by gravity may merge and give birth to something entirely different. Two graceful spirals can combine into one giant elliptical galaxy, a sprawling, roughly spherical collection of old stars left behind after the cosmic fireworks of merging subside. In other cases, a smaller galaxy might plunge through a larger one, stirring up waves of new star formation in its wake and gradually becoming part of its larger neighbor. Even on the grandest scales, collisions continue to shape cosmic structure. Entire clusters of galaxies, each containing hundreds of member galaxies, collide and merge into even larger clusters. As they do, hot gas trapped in these clusters crashes together, sending colossal shockwaves across intergalactic space. The collision of two galaxy clusters releases unimaginable energy, heating the gas to tens of millions of degrees, one of the most energetic events since the Big Bang. These cluster-scale impacts are slow-motion pile-ups that can rumble on for many millions of years. In their wake, galaxies are thrown onto new trajectories, and some stars are even ripped from their galaxies to drift alone in intercluster space. Over time, such mergers build up immense walls and clouds of galaxies, the filamentary megastructures forming the cosmic web. Gravity ensures that collisions have been inevitable ever since the universe began organizing itself. The primordial cosmos started out nearly uniform, with only slight patches of higher density. Those denser patches drew in surrounding material, growing into the first stars and galaxies. From then on, gravity's steady pull caused these newborn galaxies to congregate, occasionally bumping into one another and merging like droplets of rain coalescing on a window pane. Though we speak of collisions, these events play out so slowly that if a civilization lived on a planet within one of the merging galaxies, its inhabitants might barely notice the change over a human lifetime. Stars are so far apart that even when galaxies pass through each other, individual stars almost never collide head-on. Instead, the real action is gravitational. The orbits of stars and gas clouds shift, paths are perturbed, and great tides of matter are raised. Over time, this gentle gravitational chaos reshapes the galaxies involved, altering their forms and star distributions. If one could speed up time and watch a galactic collision unfold, it would be a mesmerizing sight. Two star cities drawing closer, warping one another with invisible tethers of gravity. Long streams of stars get flung outward, arching between the galaxies like luminous bridges, sparkling with millions of suns. In the center of each galaxy, vast clouds of gas are squeezed and collapse under the stress, igniting waves of new stars that light up like a sudden burst of cosmic fireworks. Of course, we cannot truly accelerate time to see these changes in real time. But modern astronomy has given us glimpses of cosmic collisions in progress. Powerful telescopes like Hubble have captured images of galaxies in mid-merger, tangled together in deep space. In these snapshots, we see tidal tails of stars and glowing gas arcing out, while galactic cores blaze brightly from the upheaval. Each picture is a freeze frame of that slow dance, hinting at the grand story that will continue to unfold over eons, far beyond a human lifespan. Our own galaxy, the Milky Way, has not been exempt from this grand cosmic ballet. It has quietly absorbed many smaller galaxies over its long life, growing larger with each cosmic meal. In the night sky today, faint streams of stars have been discovered. These are remnants of past mergers, the shredded remains of dwarf galaxies that drifted too close and were consumed. Far in the future, an even greater encounter awaits. The Milky Way is destined to collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor, in about 4 billion years. When Andromeda and the Milky Way finally meet, they will begin a slow embrace lasting billions of years. Stars from both galaxies will be tossed into new orbits. Some may be flung out into intergalactic space, while others plunge toward the merged galactic center. Giant clouds of gas will crash together, likely triggering a spectacular burst of new star formation. In the end, the two spirals will probably settle into one enormous elliptical galaxy, the Milky Way's beautiful spiral arms erased, but a new giant galaxy taking its place, a lasting testament to how collisions continually reshape the cosmos. For any far future observers in our galaxy, this impending collision would be an awe-inspiring spectacle. Over many generations, they would watch the faint blur of Andromeda in the night sky grow larger and more detailed, eventually stretching across the heavens as a magnificent whirl of stars. During the height of the merger, new stars and glowing nebulae sparked by the encounter could adorn the sky with unfamiliar lights. Despite the chaos on a galactic scale, our solar system might survive relatively intact, but its view of the universe would be forever changed as the familiar Milky Way transforms into a new, merged galaxy. These encounters do more than just rearrange matter in space. They act as cosmic catalysts, igniting new phenomena and dramatic changes wherever they pass. Collisions trigger transformation on every scale, from the brilliant birth of new stars amid the turmoil to the quiet death of galaxies that have spent their fuel. The true power of cosmic collisions lies not only in building the universe's grand structure, but in constantly reshaping and renewing the cosmos's contents. When galaxies interact, they often undergo astonishing transformations. A gentle gravitational encounter can compress enormous clouds of gas within them, causing those clouds to collapse and give birth to stars. During a close pass or merger, a once quiet galaxy can suddenly flare to life, with hundreds of new star clusters forming at once. Astronomers call such galaxies starbursts, their normal calm replaced by a frenzy of starbirth ignited by the encounter. In these starburst galaxies, brilliant young stars flood their surroundings with blue-white light, and massive stars live out their short lives in a blaze, exploding as supernovae. Cloudy nebulae nearby glow in shades of pink and red under the intense starlight, marking the regions where stars are forming in abundance. The entire galaxy becomes a cosmic fireworks show in slow motion, as wave after wave of star formation sweeps through its gas. Yet this spectacular phase cannot last long by cosmic standards. It quickly uses up or disperses the available gas. After only a few tens of millions of years, the frenzy dies down, and the galaxy may find itself depleted of the fuel needed for further star-making. Occasionally, a small galaxy plunges directly through the heart of a larger one, like a stone dropped into a still pond. This gravitational impact sends ripples through the larger galaxy's disk. Stars and gas are shoved outward in a great circular wave, compressing as they sweep along. This triggers a burst of star formation in a ring shape, lighting up the outline of the wave. The result is a rare and striking sight known as a ring galaxy, a luminous band of newborn stars marking where one galaxy has passed through another. Such a cosmic ripple can transform a galaxy's appearance entirely, as though a bright necklace of stars had been draped around it. Collisions also tend to drive gas toward the centers of galaxies. As two galaxies entwine, their combined gravity can funnel vast streams of interstellar gas into the merging system's core. There, the gas spirals inward toward a central supermassive black hole that may have been quietly lurking at each galaxy's heart. Awakened by this sudden feast, the black hole erupts with energy, blazing as a quasar or an active galactic nucleus. For a time, the center of the merging galaxies can outshine all their stars, beaming out intense light like a beacon visible clear across the universe. Ironically, this surge of energy from a galaxy's core can herald the beginning of that galaxy's quietus. The onslaught of radiation and fast winds from the active black hole can blow away or heat the remaining gas. Without a supply of cool gas to form new stars, the galaxy's once vibrant stellar nursery shuts down. What was a luminous starburst galaxy may, after the fireworks, settle into a subdued state. An aging galaxy with only a trickle of new stars, effectively marking the end of its star-forming life. In the aftermath of a major merger, the result is often a fundamentally transformed galaxy. Two former spiral galaxies, each originally rich with gas and active star formation, may end up as a single elliptical galaxy. The new elliptical appears as a huge, smooth ball of starlight, golden and dimmer than a spiral, typically populated by older, reddish stars with little fresh gas left to birth new ones. In cosmic terms, it's as if the collision forced a final blaze of youth before ushering the merged system into a quieter old age. The once distinct galaxies have died in form, giving way to a more stately and unchanging existence. Not all collisions play out on such grand scales. Some are tiny and fleeting, yet still transformative. In dense star clusters, two stars might stray too close and merge into a single, more massive star, briefly rejuvenating as a blue straggler that shines bluer and younger than its neighbours. Such stellar collisions are rare, but they remind us that even the seemingly steady glitter of a star cluster can hide dramatic secrets. A chance encounter between stars can create something new and unexpected. A solitary, youthful star born from an ancient population. Elsewhere, two dead stellar remnants, for example, two neutron stars, can spiral together over millennia, finally colliding and blasting heavy elements like gold and platinum into space. This kind of merger is catastrophic and brilliant. In a flash known as a kilonova, the colliding remnants forge precious metals and hurl them out into the galaxy. For a brief moment, the explosion can outshine an entire galaxy. It also sends a faint shudder through space itself, a ripple in the fabric of spacetime. Long after the light fades, that subtle tremor in space, a gravitational wave, continues to roll outward across the cosmos. If some distant civilization or a sensitive instrument is listening, they might detect this gentle whisper from across the void. The universe's very fabric carries news of the event, a nearly imperceptible ripple by the time it reaches faraway worlds. In this way, even without light, the universe quietly communicates its great changes across unimaginable distances. Such transformative events, though infrequent, have outsized importance. They enrich the universe with heavy elements that become part of new stars, planets, and perhaps living beings. In this sense, even a calamity contributes to creation. On smaller scales, collisions drive evolution as well. Countless minor impacts help assemble young planets piece by piece. And at times, a single immense collision can drastically alter a planet's path, as one did for the early Earth, knocking loose material that eventually coalesced into our moon. And so, even the most catastrophic endings can lay the groundwork for new beginnings. The debris left behind by collisions becomes the raw material for future stars, planets, and moons. In this way, one generation's wreckage serves as the next generation's building blocks, continuing the cosmic cycle of death and rebirth. In the aftermath of cosmic collisions, nothing is truly lost. Matter that was once part of one object finds new purpose elsewhere. Gas torn from a galaxy during an encounter drifts into space, but over time it can rain back down or join other galaxies, fueling future generations of stars. Even stars flung out of their galaxies during a merger continue their journey, perhaps to be captured by another galaxy's gravity, or to roam the intergalactic depths as orphans carrying light into new realms. Sometimes, the debris of a collision itself becomes the cradle for new cosmic structures. The long tidal tails of stars and gas pulled out from colliding galaxies can fragment into clumps. Within those clumps, gravity may take hold again, gathering matter into newborn star clusters or even small dwarf galaxies. In this way, a cosmic smash-up doesn't just destroy, it also creates. It leaves behind scattered pieces that coalesce into fresh formations, like seedlings sprouting after a forest fire nourished by the ashes of the old trees. On the level of individual stars, collisions and violent endings feed into the great recycling program of the universe. When a massive star reaches the end of its life, it may explode as a supernova. In a sense, a collision from within, as the star's core implodes and blasts its outer layers outward. The explosion scatters the star's elements, from oxygen to iron and beyond, into the surrounding space. These enriched gases mix with other interstellar clouds, ensuring that the next generation of stars and planets contains heavy elements forged in those stellar furnaces. We have already seen how rarer events like neutron star mergers disperse precious heavy elements across the galaxy. Those atoms of gold, platinum, and uranium, elements that would otherwise be exceedingly scarce, are strewn far and wide by the force of such collisions. In time, they drift into giant molecular clouds alongside other materials from long-dead stars. When new stars ignite within those clouds, planets will form around them, inheriting a share of this cosmic treasure of elements. Our own existence is tied to this cosmic cycle of recycling. The atoms in our bodies, the calcium in our bones, the iron in our blood, were forged in stars that lived and died long before the sun ever shone. Over billions of years, countless stellar generations and countless collisions provided the ingredients of life. We literally carry the ashes of ancient stars within us, a poignant reminder that creation in the universe often blooms from the wreckage of what came before. Galaxies themselves grow by consuming one another, and in doing so they constantly recycle stars and gas. The Milky Way, for instance, has devoured many smaller galaxies whose stars now shine as part of our own starry population. Streams of stars stripped from those past mergers are still mixing into our galaxy's halo today. What once belonged to a smaller island universe is adopted and reused, becoming threads woven into the fabric of a larger galaxy. Astronomers have identified multiple stellar streams in the Milky Way's halo, ghostly remnants of past galaxies that were torn apart. One example lies close to home. A diminutive satellite known as the Sagittarius Dwarf Galaxy is currently being pulled apart by our Milky Way. Its stars have been found in a long stream wrapping around our galaxy, gradually becoming part of the Milky Way's halo. Amidst all this visible recycling of matter, there is an unseen influence quietly guiding the process. Collisions, mergers, and even the flows of gas often follow the gravitational blueprints laid out by something we cannot see: dark matter. This mysterious substance emits no light, but it far outweighs ordinary matter in the universe by roughly 5-to-1 in mass. For every star, cloud, or atom we can observe, there is much more mass lurking unseen in these giant dark halos. Dark matter's hidden hand directs the choreography of galaxies, drawing them together along invisible filaments and shaping how they collide and coalesce. Dark matter is like an invisible stagehand in this cosmic drama, silently orchestrating movements behind the scenes. Each galaxy, sits nestled in a vast halo of dark matter that extends well beyond its visible stars. When two galaxies approach each other, their dark halos feel one another's presence first, tugging and warping under mutual gravity long before the galaxy's starry disks ever meet. These unseen halos draw galaxies together, setting them on a collision course and strongly influencing how their encounter will unfold. Because dark matter interacts only via gravity, it behaves very differently in collisions than normal matter does. Imagine two galaxies, or even two galaxy clusters, colliding. The great clouds of gas within them slam into each other and slow down, heating up and glowing in X-rays. The stars, being so far apart, mostly sail past one another without direct collisions, like grains of sand scattering in a vast emptiness. But the dark matter, being collisionless, glides straight through without stopping. In one famous cosmic collision, the Bullet Cluster, astronomers observed that most of the mass moved ahead of the wreckage of gas, as if invisible matter had ghosted through the crash. This was dark matter revealing itself by its gravitational pull, separating from the ordinary matter that was left behind. Over billions of years, dark matter's gravity has shaped the cosmic web, a filamentary network stretching across space. Galaxies are not randomly scattered, but lie along these filaments like bright beads on invisible strings. Where the filaments intersect, galaxies cluster and often collide, drawn together by the deep gravitational wells of dark matter. In essence, dark matter has built intergalactic highways, routes along which galaxies travel and eventually meet. Collisions are far more likely where these hidden roads of gravity bring cosmic travelers together at intersections. Without dark matter's guiding influence, the universe's collisions would be far more haphazard. It is the massive dark halos that often absorb and redistribute the energy of a collision, allowing galaxies to merge instead of simply ricocheting apart after a near miss. In the aftermath of galactic collisions, the dark matter halos of two galaxies, or clusters, merge into a larger halo, providing a new gravitational container for the combined system. In this way, dark matter quietly governs the ultimate fate of collisions, helping to hold the remnants together and sculpting the final shape of the new galaxies or clusters that emerge. When galaxies collide, or even brush close, they can become linked by streams of stars and gas. Gravity weaves bridges between them, luminous strands of matter drawn out from one galaxy toward the other. Through telescopes, we see these cosmic bridges as faint extensions of starlight and glowing gas, connecting two galactic systems like a tenuous rope. Such structures are a clear sign that the galaxies are exchanging matter, each tugging away some of the other's substance as they interact. One famous example is the antennae galaxies, a pair of interacting galaxies caught in the act of merging. Their encounter has flung out two long tails of stars stretching far into space, features that resemble the antennae of an insect and give this system its nickname. These brilliant stellar streamers are direct evidence of matter being pulled and shared between galaxies by gravity. To astronomers, the antennae offer a vivid snapshot of cosmic bridge building in action, frozen in a single moment of an eons-long process. Even our own galactic neighborhood bears such marks of connection. The large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, are linked by a faint bridge of stars and gas, stretched between them by past encounters. Trailing behind them is the Magellanic Stream, a river of hydrogen gas, thousands of light years long, that arcs toward our Milky Way. In the distant future, this flowing gas may rain down onto the outskirts of our galaxy, fueling the birth of new stars, a gift from one galaxy to another, delivered via an intergalactic highway of gas. For a traveler moving along one of these stellar highways, the journey would be surreal. They would depart the dense star fields of one galaxy and venture into a sparsely populated expanse lit only by the dim glow of stray stars. Gradually, the stars of the destination galaxy would grow from a hazy smudge into distinct points of light, forming new constellations in the traveler's sky. In crossing this bridge of stars between galaxies, one would truly feel the immensity of space and the gentle gravitational link that binds these distant worlds together. To an observer, these bridges and streams are ephemeral features, destined to either fade away or be reabsorbed into the galaxies. Yet while they last, they show that galaxies are not isolated islands, but share material connections, trading gas and stars through the gentle tug-of-war of gravity. Gas pulled from one galaxy can become the lifeblood of star formation in another. Star clusters tossed into intergalactic space may find a new home under the gravitational influence of a different galaxy. In this cosmic interchange, the boundaries between galaxies prove to be porous, linked by the very collisions that might seem to separate them. These intergalactic bridges remind us that cosmic collisions have a dual nature. They tear matter from one place, but seed it in another, destroying old forms while enabling new ones. The same event that wreaks havoc in one moment can create opportunity in the next. Throughout the universe, destruction and creation are interwoven, a balance struck over immense spans of time. This realization invites us to reflect on how collisions, for all their violence, are also the cosmos's instrument of renewal. Throughout the cosmos, creation and destruction are two sides of the same coin. Nowhere is this more apparent than in cosmic collisions. A mighty impact can obliterate existing structures, yet from the wreckage, new possibilities often emerge. It's a recurring theme in nature. What seems like an ending can become a beginning on a different canvas. Consider the fate of a lone star that is tossed out of its galaxy during a merger. Stripped from its familiar stellar neighborhood, it drifts into the intergalactic night with its planets, if any, still in tow. For any inhabitants on those worlds, if they could watch their sky over millennia, the tapestry of stars would gradually thin until darkness dominated most of the heavens. A once bright canopy of constellations would fade, leaving that solitary star and its tiny family of planets to wander through a quiet void. An entire solar system cast adrift, yet continuing on its journey, perhaps untouched by the chaos that expelled it. On smaller scales, collisions have also profoundly affected life's story. Our own Earth has felt this truth. About 66 million years ago, a massive asteroid struck the planet, wreaking devastation that ended the long reign of the dinosaurs. Yet in the slow aftermath of that cataclysm, new life flourished. Hardy mammals rose to prominence, eventually giving rise to humans. It's a striking example of how a destructive event cleared a path for different life forms to thrive, illustrating nature's way of finding renewal through upheaval. Even in our modern era, we have observed collisions playing out in our cosmic neighborhood. In 1994, a comet fragmented and plunged into the atmosphere of Jupiter, leaving dark bruises on the giant planet's cloud tops. That dramatic event, witnessed through telescopes, was a stark reminder that our solar system remains a dynamic and occasionally violent place. Some scientists believe Jupiter acts as a cosmic guardian for Earth by absorbing such impacts. An example of destruction in one place, potentially safeguarding life in another. In fact, we owe our very existence to cosmic collisions and explosions on multiple levels. The atoms in our bodies were forged in ancient supernova blasts and neutron star mergers, long before the sun ever illuminated the sky. Our planet's stability and seasons owe much to the Moon, which itself was born from a colossal impact during Earth's infancy. Even the mass extinction that paved the way for humanity's rise was triggered by a celestial collision. From the cosmic to the personal, it seems that turmoil and creation are interwoven at every step. These lessons of balance and renewal echo throughout the universe's grand design. The same forces that tear down and rebuild on small scales are at work assembling the largest structures of all. Every collision, from 2 asteroids to 2 galaxy clusters, contributes to the ever-evolving cosmic tapestry. To grasp the full context, we must step back and see how countless such interactions weave together the vast cosmic web that connects galaxies across unfathomable distances. On the largest scales, all of these cosmic interactions knit themselves into an immense pattern, the cosmic web. Imagine pulling your perspective far, far back until galaxies shrink to mere points of light. You would see that these points are not scattered randomly, but arranged in filaments and clusters, weaving a spidery network across the cosmos. Where many threads intersect, great clusters and superclusters of galaxies blaze brightly, and in between lie enormous dark voids, nearly empty of matter. Some voids stretch tens of millions of light-years across, with almost no galaxies inside, making even galaxy clusters seem crowded by comparison. This is the cosmic web, the grandest structure we know, a vast tapestry of matter and light, shaped by gravity over billions of years. Our own Milky Way is a tiny node in this cosmic network. It belongs to a small cluster of galaxies bound together, which in turn is part of a much larger assembly called the Laniakea supercluster, a fitting name meaning immense heaven. Within Laniakea, tens of thousands of galaxies, including our own, drift along the cosmic web's filaments, in a region about 500 million light-years across. They flow toward dense hubs and away from yawning voids, like currents in a cosmic ocean. Each galaxy's motion, each collision and merger, is influenced by the gravitational pull of this larger landscape. From this distant vantage point, individual collisions might seem like faint flickers on a colossal map, yet they are the very mechanism by which the web grows and evolves. Small galaxies coalesce into larger ones. Groups of galaxies merge into clusters, and clusters gather into superclusters, all following the guiding hand of dark matter. Over time, this hierarchical merging has built up the great walls and filaments of galaxies that span hundreds of millions of light-years. Immense megastructures like the Sloan Great Wall, one of the largest ever observed. In every dense knot and along each tenuous thread, the story of countless collisions is written into the structure we see today. Gazing at the cosmic web as a whole inspires a profound sense of wonder. There is an almost organic quality to its arrangement, as if galaxies were cells in a gigantic cosmic organism, and the filaments were its veins. The beauty of it lies in the fact that simple forces, acting over eons, have created something so vast and intricate. And within one of those countless galaxies, on a small blue world, we find ourselves trying to understand how it all came to be, and where we fit into this grand design. Amid this vast web, the question of other life gains a new perspective. If intelligent beings exist on worlds orbiting distant suns, they too are part of this cosmic web, perched on far-flung nodes of the great network. The distances between those nodes are immense. Light itself can take millions of years to travel from one cluster of galaxies to another. This immense separation underscores how truly isolated any civilization might remain, marooned on its own island of stars with no easy way to reach others. Perhaps the very structure of the universe, with its yawning voids and labyrinth of galaxies, has kept civilizations apart, each marooned on its own island of stars. It is a sobering thought. The cosmos might be teeming with life, yet too vast for living worlds to easily touch one another. In the quiet and darkness between these islands, we can only wonder, are there other minds out there, on distant worlds under alien suns, looking up and pondering the same questions that we do? In the darkness between the stars, a profound stillness seems to reign. Yet this silence is deceptive. If we could step back far enough, beyond galaxies and clusters, we would behold a vast cosmic tapestry, alive with motion. The universe is threaded with gigantic filaments of matter, unseen tendrils stretching across billions of light years. These filaments form the cosmic web, an immense lattice of galaxies and gas linking the cosmos from end to end. This cosmic web is the universe's hidden framework, a spiderweb of gravity and matter. Imagine glowing strands woven through black velvet, each strand teeming with galaxies like tiny jewels. Galaxies are not isolated wanderers. They are connected by these faint bridges of gas and dark matter. Along these bridges, like highways in the sky, galaxies and whole clusters glide slowly under the pull of gravity. Over eons, they drift and sometimes meet, converging at the crossroad nodes of the web. At those intersections of the cosmic web, the serenity of space can shatter. Here, where filaments braid together, matter pools into enormous clusters of galaxies. Dozens, or even hundreds of galaxies swarm in these regions, bound together in a gravitational dance. As filaments funnel more galaxies and gas inward, the clusters grow dense and massive. Eventually, clusters themselves may collide with one another at these cosmic junctions. What once was a gentle convergence becomes a tremendous crash on a scale beyond imagination. These collisions in the cosmic web happen in slow motion by human standards, taking hundreds of millions of years to unfold. From afar, we would see galaxies drawing nearer like swirling moths around a flame. Thin tendrils of hot gas precede them, stretching and compressing as the clusters approach. When two great clusters finally meet, the results reverberate through the filamentary bridges around them. Shock waves ripple down the cosmic threads, jostling galaxies and heating gas to extraordinary temperatures. A once tranquil corner of the cosmic web erupts into a grand spectacle of energy. Such events are exceedingly rare on the human timescale, yet inevitable across cosmic time. Over billions of years, the cosmic web has been a stage for countless mergers and collisions. Every galaxy cluster we observe today likely has a history of smaller groups that fell in along filaments, merging to build it up. In this way, the cosmic web is not a static structure, but a living, changing network. It grows and evolves through these dramatic encounters, shaping the universe's largest assemblies as time flows on. Floating in intergalactic space, one might not sense the slow drift of galaxies along filaments, but gravity never rests. In the depths of a void between web strands, things may remain quiet and still. However, within the filaments themselves, galaxies gradually gather like leaves drawn into a stream's current. They may travel for hundreds of millions of years before meeting others. And when they do meet, even in the vast emptiness, gravity binds them inescapably, and a collision begins. It is a peculiar kind of collision. Unlike cars on a highway or meteors striking a planet, galactic collisions across the cosmic web are largely governed by the unseen. Dark matter, invisible yet dominant, forms the backbone of each filament. It guides the galaxies along like an unseen hand. As clusters approach one another, their dark matter halos, enormous clouds of gravity, are the first to clash and intermingle. Long before any star or planet is disturbed, invisible gravitational tides announce the coming together of giants. Only later do the luminous components truly collide. When clusters merge, the galaxies inside are so tiny compared to the distances between them that individual stars seldom hit one another directly. Instead, the galaxies weave through each other like ghosts. A galaxy might pass right through another cluster's swarm, its stars scarcely noticing anything amiss. But not everything slips by peacefully. The diffuse gas that fills clusters cannot so easily ignore a collision. When two clusters meet, their great clouds of gas slam together head-on. It is here that the gentle glide of galaxies transforms into cosmic turmoil, releasing energy on a mind-boggling scale. At the largest scales, the cosmic web's collisions transform invisible potential energy into radiant drama. The kinetic energy of whole clusters decelerating and merging has to go somewhere. It crashes into the gas, heating it to tens of millions of degrees. Such gas glows in high-energy light, a silent beacon marking the scene of impact. In addition, as these colossal clusters coalesce, they can drive shock fronts out along the filaments, like tsunamis spreading through the cosmic sea. As a result, the cosmic web briefly lights up in those moments, edges of its filaments illuminated by the aftermath of violence. As those shockwaves surge through the tenuous intergalactic medium, they amplify invisible magnetic fields that thread the cosmic web. In their wake, electrons are whipped into motion, spiraling around the magnetic field lines and radiating energy. This process causes the cosmic web itself to glow faintly in radio waves, a ghostly whisper of the turmoil, barely detectable across the light years. Only recently have astronomers begun to catch hints of this radio glow, unveiling yet another hidden consequence of these immense collisions. Yet, ironically, to an observer on any single planet within a galaxy, these grand collisions would still appear extremely tranquil. The motions are slow, and any given star system is more likely to be carried along than destroyed outright. If humanity were watching safely from our Milky Way's vantage point, the collision of distant galaxy clusters on the cosmic web would seem a subtle change in the sky. We might notice a gradual shift in the arrangement of far-off galaxies over millions of years. Only through the eyes of powerful telescopes and careful measurements would the true intensity reveal itself. The scorching hot gas, the arcs of light from warped space, and the faint radio glow of shockwaves. The cosmic web and its collisions remind us that even in what seems like emptiness, profound events are unfolding. The largest structures of the universe grow through these occasional, tremendous unions. Every massive galaxy cluster we see today was likely forged by past mergers, countless smaller gatherings joining over time. In this way, the cosmic web is not a static scaffold, but a living network that evolves through dramatic encounters. Each collision, though unfolding over eons beyond human perception, leaves lasting imprints on the cosmos. They energize gas, warp the fabric of space, and perhaps even influence the environments in which galaxies and their stars evolve. In the grand silence of space, the cosmic web stands as both a connector and a catalyst. It links galaxies in a vast cosmic community, and at its busy intersections, it becomes a catalyst for transformation. By following the threads of this web, we uncover scenes of creation and destruction on the largest scales. We find places where galaxies, after journeys lasting billions of years, finally converge and merge. It is at these crossroads that the cosmic web truly comes alive, in the gentle glow of distant clusters and in the rare, cataclysmic flashes when those clusters collide. When entire galaxy clusters collide, the spectacle is among the most violent in the universe. In these events, thousands of galaxies, each filled with billions of stars, rush toward one another, drawn by their mutual gravity. From a distance, it might look like two shimmering islands of light drifting together. But as they meet, chaos erupts on a scale that defies ordinary understanding. Two massive clusters plunging into each other unleash energy that can outshine anything short of the Big Bang itself, transforming the space between galaxies into a furnace of roiling gas and radiation. Consider a famous example known as the Bullet Cluster. Nearly 4 billion light-years from Earth, two galaxy clusters have been caught in the act of colliding. One cluster, smaller than the other, hurtled through its larger companion at tremendous speed, a cosmic cannonball flying through a swarm of galaxies. In the aftermath, astronomers observed a scene both spectacular and telling. A bright, bow-shaped shockwave of X-ray hot gas fans out like the wake of a speeding bullet. This shock front marks where the smaller cluster's gas ploughed into the larger cluster's gas, compressing and heating it to tens of millions of degrees. It's as if one cloud of intergalactic gas slammed into another at extraordinary velocity, releasing a flash of energy across space. In the Bullet Cluster collision, the galaxies themselves fared differently. Like schools of fish merging in the ocean, most individual galaxies from each cluster passed by one another without direct impact. The distances between stars are so vast that even when galaxies overlap, stellar collisions are extremely unlikely. So the galaxies, each containing their stars and planets, largely sailed through the encounter, slowed only subtly by gravity. They continued on, leaving behind the turbulent wake of shocked gas. To an observer, the galaxy's luminous arrangements shifted positions, but did not crumble, a stark contrast to the fate of the diffuse gas that was abruptly brought to a boil. Yet the Bullet Cluster revealed something even more profound lurking in these cosmic crashes. Aside from galaxies and hot gas, there is another component in galaxy clusters: dark matter. This invisible mass does not emit or absorb light, but it carries most of a cluster's gravity. In the Bullet Cluster's collision, the dark matter from each cluster slipped past the impact effortlessly, just like the galaxies did. Unlike the gas, dark matter feels no friction. It interacts only via gravity. So as the smaller cluster punched through, its dark matter and stars moved ahead, while its gaseous content lagged behind, stuck in the collision. Astronomers mapped this event by combining telescopic eyes. They used visible light to see the galaxies, X-ray observations to see the hot gas, and a clever gravitational lensing technique to detect the mass of dark matter. What they found was astonishing. The bulk of the mass in the collision had moved past the collision point, separating from the gas. The clouds of hot gas from the two clusters were left offset from the main gravitational mass. The stars and unseen dark matter sailed through, now drifting ahead of the glowing wreckage of gas. This separation created a cosmic silhouette of the invisible, an image where ordinary matter and dark matter parted ways, allowing scientists to truly see the dark matter's influence. The Bullet Cluster collision thus became a critical piece of evidence that dark matter is real and behaves as a collisionless substance. In these cosmic pile-ups, we witness how nature's ingredients sort themselves out. The ethereal dark matter, composing most of the cluster's mass, ghosts through the encounter almost nonchalantly, dragging galaxies along with it. Meanwhile, the ordinary matter, the gas that can collide and interact, gets wrenched and left behind. It is a beautiful and ghostly scene. On an image of the bullet cluster, one can overlay the different components to see them separately. The galaxies shine in visible light. The hot gas glows brightly in X-rays, collected into a separate cloud. The invisible dark matter, for its part, is revealed in yet another distinct clump. The collision pulled apart the fabric of a galaxy cluster, laying bare its pieces for us to study. The bullet cluster is just one example of galaxy clusters in turmoil. In other corners of the universe, similar cosmic wrecks have been observed. Some carry equally evocative nicknames. There is a chaotic merging cluster nicknamed Pandora's cluster, where at least 4 clusters have slammed together in a complex mess, scattering galaxies and gas in all directions. Another colossal impact, known as El Gordo, meaning the fat one in Spanish, is one of the most massive cluster collisions known, flinging matter outward with incredible force. These names hint at the extraordinary nature of the events, a Pandora's box of mysteries, a heavyweight collision in the depths of space. In these cluster collisions, gravity's hand is both creator and destroyer. Over time, the merger of clusters will form an even larger, combined cluster, a new cosmic city of galaxies. But during the process, the tranquility of those clusters is shattered. Tidal forces from the encounter can disturb the orbits of galaxies within, potentially triggering bursts of star formation as gas clouds are jolted and compressed. Or conversely, the violence can strip gas out of galaxies, quenching their ability to form new stars. Whole galaxies can be thrown onto new paths, some flung out of the cluster entirely, destined to drift in intercluster space. The collision reshuffles the contents of each cluster, like a colossal game of billiards, played over hundreds of millions of years. Imagine the scene from a vantage point safely distant. 2 enormous collections of galaxies approach each other. Prior to impact, each cluster's galaxies orbit in a majestic, slow-motion dance around their cluster's center. Each cluster carries a halo of hot gas, glowing faintly in X-rays, and an even larger halo of dark matter enveloping it all. As they draw near, invisible gravitational forces begin to tug and stretch the clusters. When they finally collide, the first contact occurs between those unseen dark matter halos, interpenetrating without a sound. Next, the leading edges of the gas halos crash, sending shockwaves rippling through both clusters. Galaxies, like luminous grains of sand, begin to mingle. Some are deflected into new trajectories by the changed gravitational landscape. As time progresses, one cluster might pass through the other, much like the bullet cluster did. After the initial clash, they may separate, trailing debris, only to be pulled back together again by gravity for a second encounter. Eventually, if their relative speed is not enough to escape, they will merge into one. In the meantime, observers billions of years later, like ourselves, can catch the system in the act, seeing 2 distinct clusters still in the throes of merging. We might see twin cores of galaxies drifting apart with a bridge of gas connecting them, or a great arc of radio emission marking where particles are being accelerated by the shocks. The turmoil within colliding clusters is a window into extremes of physics. Temperatures soar higher than in the cores of stars. Matter moves at thousands of kilometers per second. The intergalactic gas, normally a thin, wispy presence, is suddenly ignited into a radiant blaze. Such conditions are rare in the present-day universe, and only created by these enormous collisions. Each cluster collision is an experiment set up by nature, running over vast timeframes, with outcomes that can tell us about the fundamental components of our universe. From the pandemonium of these events, a new equilibrium will eventually emerge. The chaos will settle. The gas will cool over billions of years, though likely at a higher temperature than before, permanently heated by the collision. The galaxies that were once separate clusters will now orbit within a common gravitational halo. The dark matter, ever silent, will have pooled together, deepening the gravitational well that binds the new merged cluster. What was once two or more clusters becomes one, larger and even more majestic structure. And within it, one can imagine future galaxies evolving, perhaps never knowing the violence that once brought their ancestors together. It is awe-inspiring that we can catch these clusters in the brief moments of their turmoil. The universe offers us snapshots, like cosmic traffic accidents frozen in time, that reveal forces at play far beyond ordinary experience. By studying these collisions among clusters, we delve into chapters of the universe's story that are rarely seen, chapters of chaos and transformation on the grandest scales. These rare events allow us to witness extremes of nature that we could never reproduce in any laboratory, opening a window into physics on cosmic scales. Our cosmic collisions are not only awe-inspiring spectacles, they are also laboratories for understanding the universe. In the grand experiment of nature, each crash and merger tests physical laws under extreme conditions. Unlike in a controlled lab on Earth, we cannot set up these colossal experiments, but the universe sets them up for us. By observing the aftermath, scientists can glean insights into fundamental forces and mysterious substances that would otherwise remain hidden. One of the most profound lessons has come from the collisions of galaxy clusters, the existence and behavior of dark matter. In the Bullet Cluster collision and others like it, nature performed a crucial demonstration. As we saw, the invisible dark matter sailed through the chaos, barely slowed, while ordinary matter, in the form of hot gas, was left behind, dragging its feet. This separation of matter acted like a cosmic litmus test. It showed that most of the cluster's mass does not collide in the usual way. It neither emits nor absorbs light, and interacts hardly at all, except through gravity. The dark matter's ghostly passage through violent collisions gave scientists strong evidence that it is real and nearly collisionless, confirming theories that had long been debated. Such collisions also allow us to probe the very structure of gravity on enormous scales. When clusters collide, the way their combined gravity bends light, a phenomenon known as gravitational lensing, can be measured across the merging system. If our understanding of gravity were wrong, or if dark matter did not exist, these collisions would look very different. Indeed, by examining how space is warped in such collisions, we can put our cosmic theories of gravity to a stringent test. In fact, some alternative ideas of gravity were effectively put to trial by events like the Bullet Cluster. The results, the distinct separation of mass and gas, aligned with the dark matter theory and standard gravity, Einstein's general relativity, and posed a challenge to alternatives that tried to dispense with dark matter. In this way, a distant collision in space helped confirm the invisible scaffolding of our universe and validate the laws of gravity under extreme conditions. This cosmic experiment offered compelling evidence to many that unseen dark matter truly pervades such clusters. Colliding clusters also teach us about the nature of hot plasma and high-energy processes. The shock waves generated when two clusters slam together are colossal versions of the shock fronts from much smaller events, like supernova explosions. As cluster gases, at tens of millions of degrees, rush into each other, they create bow shocks, cosmic shock fronts. that can extend for hundreds of thousands of light years. By studying the brightness and temperature of the X-ray glow from these shocks, astrophysicists can infer their speed and strength, much as we study sonic booms in Earth's atmosphere. These observations confirm that the physics of gas and shock waves, described by equations of hydrodynamics and plasma physics, holds true even at these tremendous scales and energies. Moreover, these immense collisions can illuminate the properties of cosmic magnetic fields and the acceleration of particles. When cluster shock waves plow through tenuous gas, they not only heat it, but also compress and tangle magnetic fields that thread through the intergalactic medium. In the wake of the collision, electrons caught in those magnetic fields are accelerated to near light speed. As they spiral in the strengthened magnetic fields, they emit radio waves. The result is that merging clusters often exhibit giant radio halos, or arcs, faint glows of radio energy that hang around the edges of the collision like ethereal neon signs. These shock waves give off radio emissions, which result in the cosmic web glowing in the radio spectrum. And indeed, astronomers have observed those subtle radio halos and relics. These observations prove that nature can accelerate particles to energies far beyond any human experiment. By capturing this radio aftermath from colossal cluster mergers, scientists confirm directly that shock waves in space serve as cosmic accelerators. Each collision event thus provides a wealth of information across different facets of physics. From the behavior of mysterious dark matter and the validity of gravitational laws, to the thermodynamics of ultra-hot gases and the amplification of magnetic fields, all are tested in the furnace of a cosmic crash. Our telescopes effectively read out the results of these natural experiments. For instance, the distribution of temperatures in colliding gas clouds can tell us how efficiently shock waves convert motion into heat. The presence or absence of certain radio-emitting particles can inform us about how cosmic rays, extremely fast particles, are produced in galaxy clusters. It is remarkable that by simply watching distant collisions unfold, we can infer details about subatomic particles and fundamental forces. We cannot recreate a galaxy cluster merger in any laboratory, but the universe offers them to us as experiments on a grand scale. When scientists match these observations with computational simulations, their own virtual experiments, they check whether our understanding of physics can explain what we see. So far, the major events, the post-collision split between dark and normal matter, the formation of shock waves, and the resulting radiation, all align with our best theories, albeit pushing them to their limits. Still, collisions sometimes present puzzles. For example, astronomers have found instances where colliding clusters exhibit odd behaviors that are not fully understood. Subtle differences in how gas slows down, or slight discrepancies in dark matter's distribution that make us wonder if there are new physical effects at play. Each anomaly becomes a clue, prompting deeper investigation. In this way, cosmic collisions continue to refine our knowledge. They either confirm our models or hint at new physics when something doesn't quite add up. In the grand scheme, these cosmic laboratories have helped solidify our understanding of the universe's composition. They offer direct evidence that dark matter dominates over ordinary matter on large scales. They show that gravity, as strange and potent as it is, operates the same in a turbulent cluster collision as it does in more tranquil settings. And they reveal that the energetic feedback from such events, shocks, particle acceleration, and turbulence, likely influences how galaxies within the clusters grow and evolve after the collision. In short, each crash teaches us not just one thing, but a tapestry of interconnected lessons about how the cosmos works. Through the lens of these tremendous accidents, we have been able to test the extremes. enormous masses moving at thousands of kilometers per second, matter heated to hundreds of millions of degrees, and particles accelerated to energies beyond any human-made collider. All of it happens silently in the vacuum of space, over timescales far longer than a human life. Yet by capturing snapshots from various collisions at different stages, scientists piece together the sequence of events and compare it with theory. With every new observation, a new colliding cluster discovered, a new detail measured, our cosmic lesson plan grows richer, and the universe yields its secrets a little more readily. Not all the drama of cosmic collisions is visible to the human eye. In fact, much of it unfolds in forms of light and energy that our eyes cannot see. To truly appreciate these events, astronomers tune in to different kinds of signals, from high-energy X-rays to low-frequency radio waves, and even to faint ripples in the fabric of spacetime itself. These are the echoes of collisions, and by capturing them, we gain a far richer picture of what transpires when worlds and stars slam together. When two galaxy clusters collide, one of the most striking signals comes in the form of X-ray light. The temperatures of the gas thrown into turmoil are so extreme, tens of millions of degrees, that the gas emits X-rays rather than visible light. Telescopes like NASA's Chandra X-ray Observatory have captured images of merging clusters where the glowing clouds of hot gas are clearly seen, shockwaves and all. In these X-ray views, one can observe the shape of a bow shock, the very front of the collision where gas is being compressed and heated. For example, in the bullet cluster, the X-ray image shows a bright, bullet-shaped wave of gas pushed aside by the smaller cluster's passage. Such X-ray observations reveal the otherwise invisible violence of these events. They map out the pressure and temperature of the gas, showing precisely where it's been shocked and slowed. Without X-rays, we would only see the galaxies silently moving past each other. But with X-ray vision, we witness the incandescent flash of their clash. Truly, without the X-ray view, most of the collision's fury would remain hidden from us. On the other end of the spectrum, radio waves bring another piece of the story. Long after the initial collision, as the shock waves travel outwards and dissipate, the disturbed electrons and magnetic fields continue to emit radio energy. Giant radio halos have been found enveloping some merging clusters, diffuse, faint glows that stretch for millions of light years. These halos are the residue of accelerated particles spiraling in magnetic fields, something like an afterglow of the collision. In other cases, sharp-edged radio relics, vast arcs or filaments of radio emission, appear near the periphery of the cluster, marking the location of a recent shock front. They are, in effect, the radio flash of the cosmic crash, spread out over time. Astronomers using radio telescopes have imaged several merging clusters where these radio structures stand out, confirming the presence of turbulent, high-speed electrons racing through the aftermath. The radio waves, though imperceptible to our ears, carry the story of energy transfer. They let us hear the fading echoes of the impact as particles slowly lose the energy that the collision gave them. While electromagnetic waves, like X-rays and radio, inform us of the hot gas and high-speed electrons, there is another messenger of cosmic collisions that has only recently been detected: gravitational waves. These are not waves of light at all, but ripples in space-time itself, produced when massive objects accelerate violently. For a long time, gravitational waves were only a prediction of Einstein's theory, expected to arise from cataclysmic events, such as the collision of two black holes or neutron stars. In 2015, scientists first directly detected gravitational waves, the faint quiver of space-time from two distant black holes spiraling into each other. At that moment, humanity effectively grew a new sense, an ability to hear the universe in addition to seeing it. Gravitational waves add a profound new dimension to our understanding of cosmic collisions. Certain events that might be nearly invisible in light can announce themselves loudly in gravitational waves. Two black holes merging, for instance, emit almost no light. They plunge together in darkness. Yet they send out a powerful vibration in the fabric of the universe that can travel billions of light years. When such a ripple passes by Earth, detectors like LIGO gently sway by less than an atomic diameter, and that subtle signal can be decoded to reveal its source. In the few years since the first detection, dozens of gravitational wave events have been recorded, each one the death spiral of black holes or neutron stars. These signals carry exquisite information: the masses of the objects, how fast they collided, even whether they spun. In just a few years, gravitational wave measurements have validated Einstein's predictions about such collisions. They have also revealed surprises. For example, some black holes turned out to be far more massive than previously thought. Though current gravitational wave detectors are tuned mostly to these stellar mass collisions, future instruments will listen to even lower frequencies, potentially catching waves from the collisions of supermassive black holes in the centers of galaxies. Those are the colossal mergers that happen when entire galaxies collide, and their central black holes eventually unite. Such events emit long, slow gravitational undulations that we hope to detect with space-based instruments or pulsar timing arrays. Recently, hints of a gravitational wave background, a persistent hum, have been reported, possibly arising from numerous giant black hole mergers over the history of the universe. If confirmed, it means even the grand song of galaxy-scale collisions is echoing all around us. By combining all these different signals, X-rays, radio waves, and gravitational waves, astronomers can paint a much more complete picture of cosmic collisions than by visible light alone. Each type of echo tells a different piece of the story. X-rays show us where the energy went into heating matter. Radio waves show us where particles were accelerated and how the magnetic environment has been disturbed. Gravitational waves directly encode the motions of massive objects in the collision, a pure whisper of the gravitational dance that took place. For example, imagine observing a distant pair of colliding galaxies. Visually, through an optical telescope, you might notice tidal tails of stars and gas being flung outward, a subtle sign of interaction. But point an X-ray telescope at the same pair, and suddenly you see a blaze of hot gas at their core, evidence of shock heating, or perhaps a feeding supermassive black hole stirred by the merger. Listen in radio, and you might detect synchrotron emission, proof that electrons are being accelerated in the turmoil. And if those galaxies host massive black holes that eventually merge, a gravitational wave observatory in the right band might one day hear the final coalescence, like a deep cosmic bell ringing once. This multi-messenger approach to cosmic collisions is revolutionizing astronomy. It's as if we had been watching silent movies of the universe, and now sound has been added. The full drama becomes clearer. With each collision studied in multiple ways, we learn far more than we could from any single signal. In 2017, for instance, astronomers observed two neutron stars merge, detecting both gravitational waves and a burst of light. This remarkable observation confirmed that such collisions produce gravitational waves and even create heavy elements like gold. While that was a relatively small collision on the scale of neutron stars, it exemplified the power of catching events in all channels at once. Now apply that idea to the biggest crashes in the cosmos. With galaxy clusters, we routinely combine X-ray and radio observations to study their mergers, and we use optical and infrared telescopes to chart the galaxy's motions and gravitational lensing patterns. One day, we may be able to add gravitational waves from supermassive black hole mergers to that mix. Bit by bit, the silent film of these gigantic collisions is gaining sound and color. Each new type of messenger, Each new way of sensing the universe adds depth and detail to our understanding. In the end, the echoes of collisions in light and beyond remind us that the universe communicates in many languages. To truly listen and understand, we must gather all the messages: the flash of X-rays from shocked gas, the radio sigh of fading electrons, and the rippling chorus of gravitational waves from the darkest depths. Only then do we get the full story of these majestic and sometimes ferocious cosmic events. And even as we decode these messages, we are reminded that much remains to be discovered. Beyond observing actual collisions, scientists have another powerful way to explore these events. They simulate them. With supercomputers, astronomers can effectively create mini-universes in which galaxies and clusters crash together under controlled conditions. These simulations are like time machines, allowing us to fast-forward cosmic events or rewind them to initial states. By recreating cosmic crashes virtually, researchers can test their understanding of physics and predict what might happen in the future or in scenarios we have yet to witness. One of the most famous anticipated collisions is that between our own Milky Way galaxy and the neighboring Andromeda galaxy. Though this event will not occur for about 4 billion years, scientists have already run computer simulations to visualize it. In these simulations, we watch as the two majestic spiral galaxies draw closer under their mutual gravity. Over time, they begin to interpenetrate, their spiral arms stretching and warping, stars being flung on new trajectories. In fact, few stars will collide directly. The vast distances between them mean the galaxies mostly pass through one another, but their orderly structures will be disrupted. After that first pass, the two galaxies will separate, but gravity will draw them together again. Over billions of years, the Milky Way and Andromeda will merge into a single, larger galaxy. Our night sky would change drastically during this dance. For future observers, the sky could be ablaze with new patterns of stars as Andromeda's stellar streamers mingle with our own. By feeding the laws of gravity and motion into a computer, we can witness this fate of our galaxy long before it happens, in a sped-up movie of the future. Such simulations are not limited to individual galactic mergers. Researchers also simulate the collisions of galaxy clusters and even the formation of the entire cosmic web. Huge cosmological simulations start from conditions shortly after the Big Bang and let gravity draw matter into filaments and clusters, essentially compressing billions of years of evolution into a program that runs much faster. When they play back the results, astronomers can inspect how galaxies form, how clusters assemble through many smaller mergers, and what kinds of collisions occur over the history of the simulated universe. Remarkably, the large-scale patterns that emerge from these simulations often resemble the real universe we observe. This is a strong indication that our physical theories of gravity, of how gas cools and forms stars, of how dark matter behaves, are on the right track. Simulating cosmic crashes also teaches us subtler details. For instance, by adjusting properties in simulations, like whether dark matter particles can collide with each other or not, scientists can see what effect this has on the outcome of a cluster collision. They can then compare the simulated outcome with actual observations, like the bullet cluster's dark matter distribution, to infer which properties are most likely true in the real universe. In this way, simulations become a testing ground for theoretical ideas. It's akin to performing experiments. A scientist can change a variable in the simulation, like running the universe with slightly different laws, and watch what happens. If the result looks nothing like reality, that variation of physics may be ruled out. Supercomputer simulations have grown more and more sophisticated. Early galaxy collision simulations produced basic insights, such as confirming that two spiral galaxies could merge and form an elliptical galaxy. explaining why many large ellipticals might be merger remnants. Modern simulations, however, include a plethora of effects. They track not just stars and gravity, but also gas clouds, magnetic fields, even feedback from supernova explosions and black holes that can alter the course of a collision by blowing gas outward. The highest resolution simulations can have millions or billions of particles representing matter, requiring enormous computational power. Watching such a simulation is like seeing a universe come to life in accelerated time. Galaxies form, interact, and sometimes violently collide, all according to the physical laws coded in mathematics. One benefit of simulations is that they can reach places we cannot directly observe or times we cannot rewind to. For example, we cannot witness the collision that formed a particular cluster billions of years ago, except by its aftermath. But we can simulate a similar collision and see how it unfolds step by step. We can virtually fly around a simulated collision, pause it, zoom in, and analyze every interaction in detail, something no telescope can do with an actual event light years away. This ability helps us interpret real observations. When we see a strange structure in a colliding galaxy, say, a curious plume of stars or a ring of gas, we can often find an analog in simulations and understand that it arose from a specific kind of encounter. Simulations also allow us to experiment with the future. We can ask questions like, what will the Virgo cluster, the large cluster of galaxies that includes our local group, look like in 10 billion years? And attempt to answer them by evolving a simulated version forward in time. Perhaps over that span, many subclusters will have fallen in, and Virgo will become an even more massive, relaxed cluster. We might simulate groups of galaxies on collision courses and predict how their shapes and star formation rates will change after they merge. These are predictions we won't be around to verify, but they help us understand the direction of cosmic evolution. It's important to note that simulations are only as good as the physics we put into them. When a simulation's outcome disagrees with what we see in the universe, it tells us that some physics might be missing or mismodeled. This iterative process, simulate, compare with observations, refine the theory, is a cornerstone of modern astrophysics. Through it, simulations have helped reveal, for example, that just putting visible matter and gravity into a cosmological model wasn't enough. We needed dark matter to form galaxies at the right pace, and dark energy to match the observed expansion history. By including those components, simulated universes began to look much more like the real one. In sum, supercomputer simulations serve as cosmic laboratories. They complement observation by letting us replay and dissect colossal crashes over and over. They turn hypotheses about cosmic events into visual, testable scenarios. Most beautifully, they give us a glimpse of cosmic events that are otherwise inaccessible, whether buried in the past or awaiting in the distant future. Watching a good simulation, one can't help but feel a bit of a creator's perspective, seeing eons flash by and great galaxies perform their dances and collisions. It is a reminder that, given the laws of physics, the story of the cosmos is something we can attempt to understand in its entirety, not just by observing what has happened, but by actively reenacting and predicting cosmic history through the power of computation. Cosmic collisions are not just events of the present and future. They also serve as windows into the distant past. When we observe a collision happening billions of light years away, we are witnessing something that took place billions of years ago, because the light, or other signals, from that event has taken that long to reach us. In this way, telescopes function as time machines, showing us snapshots of how the universe behaved in earlier eras. Many of the collisions astronomers have detected actually occurred when the cosmos was younger, and they reveal clues about the conditions and processes of those times. For instance, by looking deep into space with powerful telescopes like Hubble and the James Webb Space Telescope, JWST, scientists have identified merging galaxies in the early universe. JWST recently found an especially dramatic example: a system of 5 galaxies merging together just 800 million years after the Big Bang. Finding such a pile-up so early in cosmic history was a surprise. It tells us that large structures began assembling quickly. In general, the farther out, and hence back in time, we look, we see galaxies that are smaller, more irregular, and often in the process of colliding and merging. This supports the theory that big galaxies grew from the merger of smaller ones. The chaotic scenes of multiple young galaxies tangled together in JWST's images are essentially glimpses of the universe's youth, when galaxy collisions were more frequent than they are today. On an even larger scale, collisions of galaxy clusters can also inform us about the past. Some cluster collisions we observe today might be analogues of the kinds of events that were common when the first generation of clusters was forming. For example, an immense cluster collision, like the one named El Gordo, meaning the fat one, occurred when the universe was roughly half its current age. El Gordo is one of the most massive and high-speed collisions known, and it happened billions of years ago. Observing it is like reading a historical record of how energetic and massive cluster mergers could get in earlier times. It helps cosmologists check their models of structure formation. If our simulations can produce an El Gordo at the right time in cosmic history, then we know our understanding is on track. Collisions also leave marks that persist long after the event, and those marks can be used to infer past events. Consider, for example, the streams of stars and gas we sometimes find around galaxies. Often, these are the relics of a past collision or close encounter, like cosmic scars. By studying the motions and compositions of these streams, astronomers can reverse engineer what happened. Perhaps 2 galaxies grazed each other, or a small galaxy was consumed by a larger one, stretching its stars out in the process. In our Milky Way, star streams have been discovered that are remnants of dwarf galaxies torn apart long ago. They tell a tale of past mergers that built up the Milky Way over billions of years. Gravitational waves, too, carry messages from ancient collisions. The recent detection of a possible gravitational wave background, essentially a cacophony of waves from numerous far-flung sources over cosmic time, may be the combined echo of countless mergers of black holes in the early universe. If this background is confirmed and analyzed, it could offer statistical insight into how often black holes, especially the supermassive ones in young galaxies, were colliding as the universe evolved. It's like hearing the hum of a busy city from afar. You can't pick out each sound, but the overall noise tells you something about the level of activity. In a similar way, the gravitational wave background would let us gauge the general pace of massive mergers in the early epochs of galaxy formation. Every technique we have, from observing distant light to capturing gravitational waves, reinforces the notion that the universe was more tumultuous in its youth. Galaxies frequently interacted and merged. Black holes feasted and coalesced. Clusters grew through successive collisions of groups and smaller clusters. By studying collisions at various distances, and thus various ages of the universe, we can piece together an evolutionary timeline. We see that not long after the first stars and galaxies formed, they began to influence each other through gravity, merging into progressively larger structures. The cosmic web's filaments funneled matter into dense knots, where collisions became inevitable, much as we observe in clusters today. What's more, collisions can help us investigate fundamental questions about the early universe's properties. The way that colliding clusters like the Bullet cluster or El Gordo behave provides tests of whether the laws of physics, like the strength of gravity or the behavior of dark matter, were the same billions of years ago as they are now. So far, the evidence suggests consistency. The same physics applies, which is an important confirmation of cosmologists' assumptions. But if we ever observed a distant collision that didn't match what our models predict, it could hint at new physics or conditions unique to that era. In essence, each collision we observe from long ago is a chapter of the universe's autobiography, sent to us across time. By reading those chapters, we better understand how today's galaxies and structures came to be. We see that without the repeated jostling and merging, the universe would likely look far different, perhaps filled with many more small galaxies instead of the grand giants we have now. The violence of cosmic collisions, it turns out, was a creative force in assembling the cosmos we inhabit. And as we use ever more advanced observatories, we continue to extend our reach further back, finding collisions at the brink of the cosmic dawn. Each new discovery is like unlocking an earlier scene in the universe's history. Perhaps one day, we might catch the very first generation of galaxy collisions, those that set the stage for everything that followed. Until then, the collisions we can see already provide a rich narrative, bridging our present universe to its turbulent beginnings. Even with all these insights gained, we are still left with profound mysteries. The cosmos has yielded many of its secrets through collisions, yet much remains unknown. We have seen dark matter's ghostly imprint in colliding clusters, but we still do not know what dark matter truly is. It remains an invisible puzzle, quietly holding galaxies together. We have observed gravitational waves from merging black holes, but we wonder how many more exotic collisions, perhaps involving things like black hole neutron star pairs or other phenomena, are waiting to be heard as our detectors improve. Each question answered seems to open several new questions, reminding us that our exploration is far from over. There is also the possibility that nature has surprises we haven't even imagined. We have assumed that the laws of physics are the same everywhere and at all times, and so far collisions in the early universe appear to behave as expected. But what if in some corner of the cosmos, or at some extreme energy, things change? It's possible that future observations might catch an anomaly, a collision where, say, dark matter doesn't behave exactly as predicted, or a gravitational wave that signals a type of event we can't yet explain. Such a discovery would push the boundaries of our knowledge, forcing us to refine or even overhaul our understanding of physics. Our journey through cosmic collisions also sparks a sense of humility. We realize how small we are in both space and time. While we've focused on galaxies and clusters, one can't help but wonder, what about the really big picture? Could entire universes ever collide in some grand multiverse scheme? It sounds like science fiction, and indeed there's no evidence for such events. But just posing the question shows how collisions inspire thoughts that reach beyond even our own universe. It reminds us that there may be levels of cosmic structure we have yet to comprehend, and phenomena beyond our current horizon. At the same time, reflecting on these colossal interactions brings us back to more personal questions. Our search for extraterrestrial life, the theme underlying the Fermi paradox, could tie in with cosmic violence. Perhaps some civilizations out there were snuffed out by a nearby gamma ray burst from a neutron star collision, or had their planetary systems disrupted when their galaxy merged with another. Alternatively, collisions could spread life's ingredients by flinging material across space. We don't know if such factors play a role in why the skies are silent, but it shows how interconnected our cosmic story could be with these grand events. As this part of the documentary draws to a close, we find ourselves standing at the boundary between the known and the unknown. We have journeyed from the cosmic web's vast collisions down to the ripples of space-time from merging stars. And we have learned so much about the universe's workings. Yet we're also acutely aware of how much we still have to learn. Every glow of X-rays, every flash of radio waves, every whisper of a gravitational wave is a message. And sometimes those messages hint at deeper truths still veiled. It is a fitting moment to pause and contemplate the silence beyond the noise of collisions. In that silence lies possibility. The next part of our exploration will carry us forward, still guided by curiosity, still listening for signals in the dark. The universe, with all its collisions and creations, continues to invite us to seek answers. And so, with a sense of wonder and humility, we proceed, knowing that as vast and violent as the cosmos can be, there is always more mystery around the next corner of space and time.